Hello, hello, Shagato here. Welcome back to another Rust coding stream here on the 21st of December 2022. Local time 17. And let me go ahead and cut this bad boy off. I knew I should have done that. All right, give me one moment. I got lazy today and it didn't pay off. I don't know why this started happening, or I don't know how long it's been an issue, but I found that if I don't restart my Stream Deck software, sometimes certain like functions and stuff that I put on there don't seem to work. Although I'm still having an issue right now, so I might have to manually work with it. Oh, no, there we go. Okay. Sorry about that. Yeah, I don't know why that happens. It's very odd. All right, my tweet has gone out as well. And we are ready to go. Sorry about that. So what's going on here? Well, last time we did the Voronoi hive/cell map. So let's run this a couple of times and see if we get one. That's not one. That's not one. Builds from the top to the bottom. It's a pretty cool thing to watch. That's good old binary spaceport. There we go. This is our Voronoi map. Pretty cool structure there. I found it really fun to explore around a little bit. It's very hard for me to pick a favorite, but that's definitely up there. I mean, there's actually good things to say about pretty much all of these. They really do give pretty distinctive feels. So let's just a quick look at the Voronoi map that we did last time. There are a couple different algorithms there. We also had the Chebyshev distance algorithm that was mentioned. It was on the tutorial as one of the 3 supported ones, but the tutorial never put code to actually use it. And while it wouldn't be hard to make another constructor and do that, I decided to just hold off. But I did look into it a little bit, and the Chebyshev distance algorithm, I couldn't quite remember what it was, so I looked into it a little bit today during some downtime at work. And the quick glimpse I had of it was that it can be thought of like the distance a king in chess can move. So what's the shortest path a king in chess can take to get to something? So it's kind of like Manhattan distance in that you do, the over and up, right? But you can also do diagonals. So what you'd probably do is take diagonals as much as you can until you are either in line with it vertically or horizontally, and then just follow the vertical or horizontal path from there, unless the diagonal actually gets you in line with it. So that's kind of the idea of the Chebyshev distance, similar to Manhattan distance, but it also allows diagonals. The Wikipedia entry showed the chessboard, and pretty easy to follow, I think. But it's cool stuff. So I just thought I'd mention that because I remember that. And Chebyshev's theorem is another place I'd heard his name, and that popped up when I was looking around. I think that was related to calculus. I didn't really delve into it, but it looked like it was talking about the area underneath a curve or something. Chebyshev's theorem. Inequality. Oh, no, it was statistics. That's right. My bad. But the images I saw earlier made me think of calculus. That's what it was. Yeah, we're talking about standard deviations. Yeah. I saw one of these with like the colored in thing, and I just quickly glimpsed past it, and I thought we were doing area, like integrals and stuff, area under a curve. But we're not. My bad. I've corrected myself, though. As I said, it's been a long time since I've had to use any of that stuff, but I mentioned it last time. I thought we'd talk about it. Okay, let's get into wave function collapse. I'm really excited about that. I just got back from work. I just ate, and I'm ready to get started on this and see how things go. This is by virtue of just the size of the scroll bar. This is the longest chapter so far. So it may take a while, but there's also images and stuff in here. So this may be a little bit deceptive, but I'm really excited about this. I'm going to give my initial understanding of wave function collapse from some videos I've seen, and then we'll see how this pairs up with that. So my little introduction, and again, don't take this as gospel because I'm not an expert on it. I'm learning as well. But my understanding of it is, let's imagine we have a 2D grid. Let's just imagine, similar to what we're going to have in this game. We have a 2D grid and we're trying to build a map out of it. So what we can do is we can basically start out by saying every spot on the grid can be one of any number of tiles that we've kind of defined as possible tiles. So what I mean by that is, let's be really simple and say, like we have sand and sand. We have sand and water and grass and trees and maybe mountains or something. So we have like 5 different tiles. That means every spot, every tile on the grid can have one of those 5 different options. And then what we do is we can randomly pick one tile on the grid and assign it something at random. So let's say we assign it sand. Well, so what we've done now is sand has some information with it, because this is part of like how you define your algorithm, basically. We would say maybe sand can only be next to grass and water, with the idea being it's like a beach. So you go from sand into water, or you go from sand into like grass and stuff. And this is a simple version, but then if we pick a random tile and we assign it sand, then all of the neighboring tiles can no longer have 5 possible options. They can only have 2 possible options: water and grass. So what we've done is we've reduced the possible domains of those neighboring tiles of the sand into water and grass. And then maybe grass can be adjacent to trees and mountains or something. So then if one of those gets turned into grass, then all of its neighbors now have... Actually, I shouldn't say... I should make one extra caveat. So we actually probably would have reduced the domain to 3, not to 2, because it would probably be water, grass, and sand. Sand can probably be adjacent to more sand. But you get the idea, right? So whatever the valid possible neighbors of a tile type are, that reduces the domain of all the neighboring tiles there. And so as you keep going through and basically randomly picking these tiles in the pieces of the grid on the map, and then randomly assigning something from its valid domain, you kind of build up a little bit of a map there. So that was an example that I saw that's very high level, but it looks like, just from having skimmed this in the past couple of lessons, it looks like there's going to be some tiles and stuff that we're defining here. And what we may actually be doing is defining structures that are not just one map tile wide, but maybe an entire small house or an entire room or something. So we may be defining larger structures and then saying, well, this can, go next to a hallway. This room goes next to a hallway or another room, right? So we may be doing something like that. So I'm eager to see how it works. It seems like it's going to be a lot of fun. And I do also recommend the video that I'm really referencing, and it uses similar demonstrations to what I just described, is something like why I'm using wave function collapse. And we'll go over there real quick, just to show it. Why I'm using wave function collapse for procedural terrain. So just to give credit, so these modules here are like the tiles that I was mentioning, and you basically define how they get to fit together. And so some of the examples were like what I was talking about with sand and trees and grass and stuff. So this is what I'm kind of basing my ideas off of. And it's a cool video to watch, and we can end up with simple maps like this. Now, this is very, very simple, and you'd want to have some like nicer rules to make something a little bit more orderly. Because as we see here, it's kind of just throwing water in all kinds of random places, but it's following these rules that are pretty easy to set up. So I'm very interested in doing this. Now, enough of me saying that. We're 10 minutes in. Let's get started. A few years ago, wave function collapse, WFC, exploded onto the procedural generation scene. Apparently magical, it took images in and made a similar image. Demos showed it spitting out great-looking game levels, and the amazing Caves of Cud started using it for generating fun levels. As an aside, I am currently playing Caves of Cud on my Friday and Saturday night streams, and I love it. It's a great time. I did not realize that they used it. One of the other things that I've seen wave function collapse, in that same video, they show how you can do textures with it as well. So that's another thing to look out for. The canonical demonstrations, along with the original algorithm in C# and various explanatory links/ports, may be found here. So we have this GitHub here. Ah, that's it. These little like plant things here, these are actually shown on that video. So take a look at that video. This program generates bitmaps that are locally similar to the input bitmap. Yeah, so we have 3 little houses here, and we get these larger villages. Tiny little mountain thing. Here we have some generated. Yeah, this looks like a level maybe that we might be building, or I don't know what this is supposed to represent. It's cool though. When did this first show up? What is can we see the earliest commit? Rather like the origin of this repository? Whatever. we'll think about that later. Okay. In this chapter, we're going to implement wave function collapse from scratch and apply it to making fun roguelike levels. Note that there is a crate with the original algorithm available, WFC accompanied by WFC image. It seemed pretty good in testing, but I had problems making it work with WebAssembly. I also didn't feel that I was really teaching the algorithm by saying, just import this. It's a longer chapter, but by the end you should feel comfortable with the algorithm. And another personal aside, I know we're taking a long time to get started here, but another personal aside is, I said this before, but if you're trying to learn an algorithm, I personally recommend implementing it yourself. When I was in university, we implemented linked lists, which I guess everyone probably does that. We implemented hash maps ourselves. We implemented, like, I'm blanking on other data structures, queues, stacks, stuff like that. We implemented a lot of those basic data structures ourselves as a way to make sure we really understand how they work. And then obviously when we're making real programs, we use the ones that come in our standard libraries. But to learn the algorithm, try making it yourself. Go look at the original, re-implement it. For many of these algorithms, you can go on Wikipedia, and Wikipedia may not be the gospel always, but usually there's pretty good pseudocode on there, and you can follow along with the pseudocode and try implementing it yourself. So do that, and then try using these crates after the fact. So what does WFC really do? Wave function collapse is unlike the map generation algorithms we've used so far, in that it doesn't actually make maps. It takes source data in, will use other maps, and scans them and builds a new map featuring elements made exclusively from the source data. It operates in a few phases. It reads the incoming data. In the original implementation, this was a PNG file. In our implementation, this is a map structure like others we've worked with. We'll also implement a Rex Paint reader to load maps. 2, it divides the source image into tiles, and optionally makes more tiles by mirroring the tiles it reads along 1 or 2 axes. 3, it either loads or builds a constraints graph. This is a set of rules specifying which tiles can go next to each other. In an image, this may be derived from tile adjacency. In a roguelike map, connectivity of exits is a good metric. For a tile-based game, you might carefully build a layout of what can go where. 4, it then divides the output image into tile-sized chunks and sets them all to empty. The first tile placed will be pretty random, and then it selects areas and examines tile data that is already known, placing down tiles that are compatible with what is already there. Eventually, it's placed all of the tiles and you have a map/image. There we go. So let me reiterate point number 4. It divides the output image, which for us is going to be a map, into tile-sized chunks and sets them all to empty. The first tile is random, and then it selects areas and examines the tile data that is already known, placing down tiles that are compatible with what is already there. So that's basically what I described earlier. So I definitely think I had a good understanding of the algorithm, and I hope that the double explanation helps. The name wave function collapse refers to the... Yeah, and this makes sense too, by the way. So before I even read on, the idea that I got from wave function collapse is that if I saw the YouTube video up, what you may have noticed is there was the grid. In fact, we could just pull it up real quick. There was the... don't slide when I'm clicking things. This grid here is showing the domains of how many possible tiles there can be. So what we see here is this one's already set, so it's only one. And now that means the neighboring tiles only have 3 possible tiles. But then based on those 3, those neighbors have 4 possible tiles. So what's happening is as you're assigning more and more tiles, think of it like they were just mentioning quantum physics, QED, quantum electrodynamics, whatever you want to call it, quantum mechanics, a bunch of fancy names for largely the same idea. The idea that as you observe something, it collapses into a specific state is kind of what we're doing here. Because then as we assign the next tile, let's see, as we assign these other tiles, all the other ones are also updating their domains. And then we see over time, some tiles will have no choice but to be a specific type. So that's the idea of how we're kind of collapsing. And at a point, you may end up with a very simple loop over the map without having to do any random decisions, because there may only be one option for all your remaining tiles. The name wave function collapse refers to the quantum physics idea that a particle may have not actually have a state. Okay, that's weird. Refers to the idea that a particle may not actually have a state until you look at it. In the algorithm, tiles don't really coalesce into being until you pick one to examine. So there is a slight similarity to quantum physics. In reality, though, the name is a triumph of marketing. The algorithm is what is known as a solver, given a set of constraints. It iterates through possible solutions until the constraints are solved. This isn't a new concept. Prolog is an entire programming language based around this idea, and it first hit the scene in 1972. So in a way, it's older than me. Yeah, Prolog is interesting, by the way. I only had a little bit of exposure to it in university, but I quite liked the look of it. Get a quick link to the wiki. It's very logic based, so it's actually considered logic programming language. And go figure, the thing that got me into computer science, artificial intelligence, is also related to it. That's why I got a bit of exposure. It's also where I got my exposure to Lisp. So we can see it's very, very different than what we're dealing with in Rust, because we basically generate like different rules and such. Clauses, right? Clauses with bodies are called rules, and we can add rules and ask what things are animals, all kinds of weird, interesting things you can do in Prolog. All right. Getting started, Rust support for complex modules. All our previous algorithms were small enough to fit into one source code file without too much paging around to find the relevant bit of code. Wave function collapse is complicated enough that it deserves to be broken into multiple files, in much the same way as the map builders module is broken into a module. Wave function collapse will be divided into its own module. The module will still live inside of map builders, so in a way it's really a sub-module. Rust makes it pretty easy to break any module into multiple files. You create a directory inside the parent module and put a file in it called mod.rs. You can then put more files in the folder, and so long as you enable them with mod my file and use the contents with use my file my element, it works just like a single file. So to get started inside your map builders directory, make a new directory called waveform collapse and add a file mod.rs into it. So we actually did this already, of course, to make the map builders, so it's really not that much different. All right, waveform collapse. And then we're going to do mod.rs. And we'll populate it with a skeletal implementation similar to previous chapters. So I'm going to copy that and we'll just skim over it real quick, but it doesn't look like it's going to be that special if we're being honest. Now in here, I think we need to do mod waveform collapse. That way this thing will, is hash map not in here? That's weird. That is a bit weird. I copied their code, but it's, and it included their use, but it doesn't have hash map. Okay. All right, so we're bringing in Voronoi spawn regions. Second, all right. Yeah, we're bringing in Voronoi spawn regions. Just a couple, some things from common. Basically, general map stuff, not very exciting. So we're going to have our builder, which is pretty standard right now. We haven't added anything special to it. Map, starting position, depth, history, noise areas. Then the basic functions. Well, we have to do these because it's an impl map builder. So this is not anything new. And then this is where it's going to be more interesting. We have a skeletal builder here, or a skeletal build function here. Let mute RNG. Builder goes here. We do our starting position. We do our exit tile with the unreachable areas. Where is start index? It's commented out. Is this the one that, this is from the what's it called? The maze. No, not the maze. Was that from DLA? I remember doing this. This just keeps walking left until it finds an open tile. And that's our starting index. We're going to do this one here. That's also... Oh. Okay, let's go... How do I do it? Home? Alrighty. Let's just do that for now to keep it from being mad. But yeah, nothing really special here. I think we can get back to the tutorial, not waste any more time. I mean, it's just a skeleton. We've seen this. Now, we'll also modify map builders. Yeah, we're going to do this. I'm just going to go do it. You can trust that I've done it right. Because it's not really special, is it? And failed to resolve waveform, so I'll import it. Which is standard. We've done that for all the others. All right. Like I said, you didn't really need to see me do that. It's a copy paste. Just to comment all those out and bring in the new one. So we've got an empty map, all walls if we cargo run, but it's a good starting point. Well, let's check it out, I guess. Not very exciting. Oops, I clicked the wrong thing. You don't see it, but I clicked the wrong thing. Boom. Okay, we're done. Wave function collapse is here. Oh, no. I mean, we're using the waveform collapse builder. It must be it, right? It must be done. All right, now the exciting stuff. You may remember back in section 2, we loaded a Rex paint file to use as the main menu screen. We're going to do similar here, but we're going to turn it into a playable map. It's a deliberately odd map to help illustrate what you can do with this algorithm. Here's the original in Rex Paint. So Rex Paint is actually a program. You can see it here, it's a little small, but it's actually a program that allows us to draw. So I do like this because it's similar to like a sprite sheet or something where we can actually draw out images and such, and then we can use this. In fact, I think we might actually be using it like a sprite sheet. So another quick aside, if you're not familiar with sprite sheets or what sprites are in general, sprites are not as commonly used today, but they are still used depending on what kind of game you're making. But especially back in the day, sprites were used for like the images that you had on screen. So you had a character, and what you were seeing was their sprite, and all the animations and stuff would be built from a sprite sheet. So you would have like a sheet that looks, let's just imagine it's something kind of like this. Actually, even better, Sonic sprite sheet. Look at a Sonic sprite sheet. And so this is an example of how a sprite sheet would look. We have all the different things that Sonic can do, all the different animations and everything. And what we do is programmatically, you can rip these apart. Zoom in a little bit. Oh, it's not going to zoom in. View file. So programmatically, we can actually rip these apart and build up the build up the frames of animation and then play them back in the game. So we essentially kind of define the coordinates of each like frame of the sprite, and we just rip those out, and then that's what we see in the game in playback. And so here we have like the spin animation made up of all these different frames here. You know, we have this like snowboarding animation, have this like running animation, supersonic like dashing or whatever. So this is how we kind of build these out. So it looks like we're going to be doing something a little bit similar, or at least that's how I think we're going to be going. So except here we're kind of painting in little rooms and stuff, and then we'll be defining how to work with those. So he says, I've tried to include some interesting shapes, a silly face, which we see here, plenty of corridors and different sized rooms. Here's a second Rex Paint file designed to be more like the old board game, The Sorcerer's Cave, of which the algorithm reminds me. Tiles with 1 exit, 2 exits, 3 exits, and 4. It would be easy to make these prettier, but we'll keep it simple for demonstration purposes. Oh, okay. I see. We don't have any more images, but you can kind of see what's going on there. 4-way. This looks like it has maybe just 2, although there's some connection going on there, whatever. Okay. These files are found in the resources directory as WFC demo 1. Okay. Let me go grab those. Is Control-Shift-K duplicate here? I don't see a duplicate hotkey. All right, let me deactivate the browser. You won't see anything anyway, but you won't see the pop-ups, but just deactivate it for a moment. Where is it? Resources. And what do we need? WFC demo 1 and 2. Okay. There's also WFC populated. I don't know if we're going to need that, but I'm going to download it as well. And yeah, repositories, coding stream 30, resources, boom. And I'll dump the other 2 in there. So you see we have all 3. Literally just navigated to the Rust Roguelike tutorial /resources and found the 3 WFC ones there. Again, only the first 2 were mentioned, but well, it seems like this one might also be used. Just logical deduction. All right, and now we're going to modify rexassets.xp to include these files. So let's go and do that. It's been a hot minute since we touched that. I believe that was for our title screen. We can also see resources here that they are now included. Where was it at? I just saw it a moment ago. Wait, so we have .xp? Is it in the resources folder? Yeah, I don't think we have a rexassets.xp, but we do have this. I think that's a slight typo. Just to be clear, the tutorial text says modify rexassets.xp, but the code there is this file, rexassets.rs. So just making a note there of, you know, why I'm doing what I'm doing. So we got a couple more of these to add. And we're going to call this WFC demo image 1. In fact, I'm going to just do that because I don't want to type that again. Demo 2. And this is going to be that and that. Beautiful. And now in the Rex assets down here, we need to pull those in as well. We need to link the resources. So it's just going to be demo image 1 and 2. But we're not actually getting those out yet. So I guess we're going to pull those in just in the wave function collapse side, and we're not going to pull them here with this like Rex assets. So we'll take a look at that. The tutorial continues on. It's just a one-liner, so I won't switch over. Finally, we should load the map itself. Inside the waveform collapse directory, make a new file, image loader, waveform collapse, new file, image loader.rs. And we're going to do some interesting stuff. Okay, use rltk rex xp file. We're going to bring in map and tile type. Loads a RexPaint file and converts it into our map format. So pub function load rex map. It's going to take a reference to an XP file and our new depth. So new depth should be pretty familiar. Interesting that we're seeing that here in our image loader. I'm curious what new depth is going to do here. Oh, it's because we need it to make a map. I find it a little interesting. I almost think it would be nice to decouple that. It seems that although we need it to make a map, perhaps it would be better to pass a new map in here rather than passing in the new depth. But then you also rely on ensuring that the user passes in an empty map or passes in a new map rather than one that's been all jacked around with. Okay, so we're doing a loop over the layers. So we've got a triple for loop here, but what we're doing is the XP file has layers. And then for every layer, we go through the width and the height. Just a simple a double for loop to loop through the entire map, basically. Nothing special about it. Let's cell equal layer.get xy.unwrap. Don't like unwrapping, but hey, we'll do it. And we're just checking the X and Y values to make sure they're not going to go out of bounds. Convert that into our map index format, which we've seen a million times now. I don't think those are both supposed to be pound signs. They are, and I think the idea is to show what it would look like in game. Would it be a pound sign or something else? The empty one for the floor. I guess that's what the comment's for. I'm just copying what's there. That's really it. And then at the end we return map. I'm genuinely curious about something. Because we have multiple layers, I think we used that when we did the main menu. And it was a way to simulate a higher resolution image than we could actually really support by layering information. I think we rendered it at like, I think the image is like half size, but it has 2 layers to build in extra info. I don't remember exactly how it worked now. Are we just assuming that we only have 1 layer? Or in the case that we have multiple layers, are we going to be potentially overriding these cells? I mean, I guess we will, but it's just interesting to think about what would happen in a case like that. I think this is pretty self-explanatory, though. As I mentioned, for every layer, we simply loop through all the tiles, all the XY coordinates of it. We convert it to a cell. Well, not convert, but we get that. Okay, yeah, let's see. Let me go into here and just say real quick, mod image loader. That way we can get some extra info here. So layer, it's a vec of XP layer and global. So this layer is an XP layer. And layer.get XY is just the cell at coordinates. So just think of it as an individual piece of the grid, an individual cell in a chessboard or whatever, right? And that's an XP cell. And then what is .ch? It's the character index. Because Rex Paint is just ASCII characters in the end. So cell.ch is just the character, and that's what we're matching on here. Which character is it? Okay. Now, I don't know if this is exactly where we want to have the mod being pulled in. Image loader. So we'll work on that at some other point. I just wanted to get some extra context there. All right. So let's go back over to the tutorial where we are making progress. So we just did this. And they say this is really simple. And if you remember the main menu graphic tutorial, it should be quite self-explanatory. This function accepts arguments for new depth because maps want it, and a reference to an XP file, a Rex Paint map. It will be made completely solid, walls everywhere, by the constructor. It creates a new map using the new depth parameter. For each layer in the Rex Paint file, there should be only 1 at this point. For each Y and X on that layer, and that's critical. There should only be 1 layer at this point, but I'm just thinking about it would be interesting if there's not. For each Y and X on that layer, load the tile information for that coordinate, ensure that we're within the map boundaries in case we have a mismatch in sizes, calculate the tile's index for the cell, and then match on the cell glyph. If it's a pound sign 35, we place a wall. If it's a space 32, we place a floor. Now we can modify our build function in mod.rs to load the map. Okay, so let's take a look at it. And mod.rs, we have 2 mod.rs's, which can get confusing. Builder goes here. So we're going to load from resource. And this might be an issue. Theirs has 2 backs. I think ours only needs to go 1 back. Because I think I formatted mine slightly. We'll have to check. So we'll just try to load that image. And now we'll import everything. Oh no, okay, so let's go up to the top here and go ahead and do it. What was it? Image loader. And then we should be able to pull that in. Now we're not going to know yet if that's valid until I try running it. Well, we can take a look though. It's got to go. That's not from where we're at, but I think it goes. I think it's running like from the source directory. So we just should go back one and then we should be able to hit resources. I think that's how it's set up. And I think on theirs they have to go back twice, so they have // a second time. But they have theirs set up in a way that has each lesson in a separate module, basically. And we're not doing that. We're going to take a snapshot, and then we do the find the starting point, and self.starting position self.map.width over 2 and height over 2. Yeah, that's all the same. It was showing up, so I wanted to make sure. At the top, we'll have to tell it to use the new image loader file, and they're doing something different, so let's actually get rid of that. Do mod image loader, and then just use everything. And now if we run it, we should be good, but we'll take a look in a moment because there's some more info. Note that we're not putting pub in front of these functions. We're using them, but not exposing them outside of the module. This helps us keep our code clean and our compile time short. In and of itself, this is cool. Now we can load any Rex Paint designed level and play it. If you cargo run now, you'll find that you can play the new map. Yeah, so let's check that out. I'm excited about that alone. That opens up many, many possibilities. If you decide that you want to have a specific hard-coded map for like the last boss or something, that would be a great way to do it. Paint the map yourself and then load it in. There we are. Look for the little face. Oh, I'm getting lost on the way there already. Ah, here's our face. There we go. I think it's pretty self-evident that it worked. So I don't think we need to spend more time here, as fun as it is to walk around and unveil the map. Let's not waste more time, right? So we'll make use of this in later chapters for vaults, prefabs, and pre-designed levels. Called it. And we actually see both of these are the next 2 chapters. I looked immediately as I read that. I was like, wait, when is that? Like next? But for now, we'll just use it as source data for later in the wave function collapse implementation. So now we're going to carve up our map into tiles. Again, this is just like the sprite sheet, basically. We discussed earlier that wave function collapse works by carving the original image into chunks/tiles and optionally flipping them in different directions. It does this as the first part of building constraints, how the map can be laid out. So now we need to start carving up our image. We'll start by picking a tile size. We're going to call it chunk size. We'll make it a constant for now, but it'll become tweakable later. And start with the size of 7, because that was the size of the tiles in our second Rex demo file. We'll also call a function we'll write in a moment. Okay, so let's do that. And if you didn't notice, the next thing is basically a one-liner before the next bit of code, so I'm not going to click back over just to show that as I read it. So at the top of build here, chunk size is 7. After the snapshot, there we go. And now build patterns is obviously mad, but we'll fix that. So it says, since we're dealing with constraints, we'll make a new file in our map builders waveform collapse directory, constraints.rs, and then we're going to make a function called build patterns. So I'm going to just preempt it by saying mod constraints and use constraints everything, and then new file constraints.rs. Now in here, we'll pull in a couple basic uses. We're gonna do a hash set, which I think we've seen them in this tutorial, but it's been a while. And this is a public function. Build patterns, it's a map. Chunk size, include flipping, dedupe. And it does return what dumb thing did I do? I was like, I know I didn't close something, but I was like, what did I not close? Okay. So let's get in here now and start writing this bad boy. It's a beefy boy. So we're dividing the map into chunks. So we do X and Y based on the width and height respectively, divided by chunk size. Easy. And we make our patterns vector, which is just going to be empty. Now I'm going to confirm if we're just returning patterns at the end. Watch this vec unknown. It is now magically got a type. Okay. Yeah, we're fine. It's complete. I was just curious about the returning the result of a let binding from a block, but no, we don't got to worry about that. I was just interested in what it was saying. I knew it wasn't a problem because we haven't written anything yet. For cy in 0 to chunks y, guess what we're going to do with x? Same thing for cx. Normal orientation. So I think what dedupe is going to be is we're probably going to be looping through the final results and maybe comparing them to see if there are... Imagine if you had one that's just a very simple square room that's like, you know, no matter what way you flip it is the same. That would be an example of something you would dedupe, you would deduplicate by saying call some of those, right? Because then if you flip it, you've got like all these different combinations of it that are all identical. So normal orientation, we're going to make a pattern, a vectile type. Oops. So hopefully this is pretty easy to follow, but let's break it down a little bit anyway. The start and end x, what we've done here with the chunks x and y, we've determined how many chunks fit on the map, right? By dividing the width and height by the chunk size. So then every iteration of these variables, cx and cy, as they're going through chunks x and y, every one increment of that is saying that's how many chunks we're moving over. So cx times chunk size gets us where we're at on the map, and then cx plus 1 moves us to the end of that chunk, well, again, times chunk size moves us to the end of that chunk. So we're doing that with x and y, basically defining the boundaries of that spot on the map. Again, akin to the sprite sheet, we'd be drawing a box around one of those Sonic sprites. That's what we're doing here, but we're drawing a box around pieces of the map. Is it gonna, yeah, okay, good. I didn't like that spacing on the first range there. Map.xy index, some things never change. So what we're doing is we're literally just pushing those tiles, the contents of the tiles, you know, whether it's a wall or a floor or whatever, we're just pushing that into a vector. Pretty simple. Not much to it. The thing is, we're going to have to traverse that as a 2D vector. So that's going to be based on the chunk sizes, because we don't want to go over for the entire map width. We want to go over for the chunk size right now of 7, what we defined earlier. But we did take it in as a variable, so it's going to be fine. But that's kind of how we use it now. It's just like a smaller version of our main map. We're just treating it as a little mini map, if you will. So it's still going to kind of have to do the same map XY index thing, just based on a chunk size instead of the overall map. There's a loud sound outside. It startled me. You probably don't hear it, but alrighty. So we push that in there, and then we push the so we push those into the pattern, and then we've built the entire pattern, so we push that vector into patterns. Now if we're including flipping, we need to flip a couple of different ways here. So first, horizontal. Okay, so there we go. Similar to what we did before, we are fixing the Y value because we're flipping X. So we do a little bit of math here to say end X minus X plus 1. This is one of those things where the best way I can explain it is to say draw a picture and see how this actually works. I find it a little bit difficult to explain, but once you kind of draw a picture and see how it works, it's not that difficult. It looks like magic numbers, but it's not that bad. So we're flipping horizontal. Now we're flipping vertical. And you might be able to guess we're going to do something very similar. We're still going to loop from Y to start and end and X to start and end. None of that changes. But if we fixed Y before, now we're going to fix X in a single position. And we're going to do end Y minus Y plus 1. And then we do the same thing where we push that new pattern into the patterns vector. And now we flip both. And you might be able to guess how that one's going to look. And this is something similar to what we've already seen in the DLA, right? DLA and was it also Drunkard's Walk? Did we do symmetry in that one? I don't remember. We may have done symmetry in Drunkard's Walk. Fearful symmetry, yeah. So in a couple places, so in Drunkard's Walk, we added symmetry after we did it with DLA. And then like the insectoid and stuff uses symmetry. Oops. Let's not do that. So there's going to be a lot of similarities here in how that works. So that's not quite it yet, but we're almost done. Basically, though, the general idea is, just to again make it clear, is if we're flipping horizontal, we keep y in the same direction, and we simply kind of reverse the x values. And we do the same if we're flipping vertical, but we reverse the y values, or we reverse both if we're flipping both. And then we dedupe. I always kind of like dedup without the e, but it's fine. If dedupe so pre-dedupe, deduplication, there are blank patterns. And then we're making the hash set. Ah, that's an easy way to do it. I forgot we included that, but that's an easy way to just kind of get that mostly for free. I mean, there's still work going on under the hood, but... Oh, they actually did dedup on that comment, by the way. What's going on, Tusk? So very simple. What did I do here? Oh, it's .len. My bad. And then patterns.drain. Oh, we don't. Okay, we need to go implement hash for the tile type. Where is tile type? Get hash over here. Okay, so just a very quick explanation. I think we've used a hash set before, but just to make sure, a hash set. So a set is like a mathematical thing where basically everything has to be unique, right? So a hash set is a store that makes sure we don't have any duplicates. So a hash set implemented as a hash map where the value is just the unit type, the empty tuple there. If two keys are equal, their hashes must be equal. I don't really see a good example, but basically what's going to happen is if you insert two identical things into the hash set, it's just going to basically ignore. It's going to get rid of the duplicates for you. So drain is a way to basically remove the specified range from the vector in bulk, returning them as an iterator. So we're doing a little bit of a fancy thing here, which there's probably other languages that do this as well, but very cool in Rust, where we're just saying drain the whole thing with the double dots here. It's called range full. So just drain all of it, but give us that iterator, and we do collect. We've specified that we want it in a hash set, so it automatically builds that hash set for us. which is getting rid of the duplicates. And then we extend patterns, which we just drained. So extending takes an iterator and puts all that stuff into it. So we're basically just moving it from one thing into another, which gets rid of the duplicates, and then moving it back in. It's a very interesting way to do it. And then we're just logging before and after how many things are in the patterns, how many patterns we have, right? Let's take a look over here. That's quite the mouthful of a function, so let's walk through it. At the top, we're importing some items from elsewhere in the project. Map, tile type, and the built-in collection hash map. We declare our build patterns function with parameters for a reference to the source map, the chunk size to use, tile size, and flags, bool variables, for include flipping and dedupe. These indicate which features we'd like to use when reading the source map. We're returning a vector containing a series of vectors of different tile types. The outer container holds each pattern. The inner vector holds the tile types that make up the pattern itself. We determine how many chunks are in each direction and store it in chunks X and chunks Y. We create a new vector called patterns. This will hold the result of the function. We don't declare its type because Rust is smart enough to see that we're returning it at the end of the function and can figure out what type it is for us. Then we iterate every vertical chunk in the variable cy, and we iterate every horizontal chunk in the variable cx. We make a new vector to hold this pattern. We calculate start x, end x, start y, and end y to hold the 4 corner coordinates of this chunk on the original map. Side note, that's again like the Sonic sprite sheet that I showed earlier, drawing that box around the chunk, or drawing that box around Sonic. We iterate the pattern in y/x order to match our map format, read in the tile type of each map tile within the chunk, and add it to the pattern. We push the pattern to the pattern's result vector. If include flipping is set to true because we'd like to flip our tiles, making more tiles, repeat iterating y/x in different orders, giving 3 more tiles. Each is added to the pattern's result vector. If dedupe is set, then we are deduplicating the pattern buffer, basically removing any pattern that occurs more than once. This is good for a map with lots of wasted space, if you don't want to make an equally sparse result map. We deduplicate by adding the patterns into a hash map, which can only store one of each entry, and then reading it back out again. For this to compile, we have to make tile type know how to convert itself into a hash. Hash map uses hashes, basically a checksum of the contained values, to determine if an entry is unique and to help find it. In map.rs, we can simply add one more derived attribute to the tile type enumeration, and we see here the hash, which I did already. This code should give you every 7x7 tile within your source file, but it would be great to be able to prove that it works. As Reagan's speechwriter once wrote, trust but verify. In constraints.rs, we'll add another function, render pattern to map. Okay, let's get to it, because we're not even halfway done. All right, this is not a public though. Render pattern to map. It takes a map, mutable reference to a map. Chunk size I32, and stuff that I can't read. I have to scroll. Start X. And it does not return anything because we're actually just drawing on the map, or we're modifying the map. So that's one way to do it. We could have also just specified the type, and instead of saying 0 usize, we could just say 0. Or we could maybe just ignore it and see what would happen. All right, let's break down what's happening here now. Um, we're passing in a pattern, which we know is just a vector of tiles. And we have to basically, we are using the XY index to convert that to like actual map coordinates, which I did mention before. But basically what we're doing is we're checking if I can get away with this. Yeah, it still knows we need a U size. I'll leave it anyway, but so we're setting I to 0. We're looping through the tiles of the pattern, and we are using chunk size, as I mentioned before. And that gets us a tile Y and tile X. That's basically where we're at on the loop so far. So then our map XY index is converted with this start X and start Y, which are passed in, plus the tile X and tile Y. That's how we're getting our map index there. Which is implicitly, again, based on the chunk size as well, because of the loops, right? So then map.tiles of that map index is now the, it's the corresponding tile from the pattern. So then at the end, we increment I, that's basically just going to the next tile in the pattern, right? And then map.visible tiles, we're setting it to true. So pretty straightforward. We haven't had to do that in a while. I wonder why we're making it visible. Am I forgetting? We'll worry about that in a minute. Okay. So this is pretty simple. Iterate the pattern and copy to a location on the map, offset by the start X and start Y coordinates. Note that we're also marking the tile as visible. This will make the renderer display our tiles in color. Okay, that's I was thinking it was probably just for show. And also, yeah, that's another thing I meant to mention, but when we're passing in that start X and start Y, that's where we're actually drawing it on the map, right? That's what I was kind of trying to say earlier. That's where we're drawing it on the map, is the start X and start Y, but then these tiles, X and Y, kind of get us through the chunk itself, which is going to be our pattern. They get us through our pattern itself, rather, which is, again, kind of bound by the chunk size. So we're going to go from start X, we're going to go over. Again, if our current chunk size is 7, we're going to draw 7 over. Then we're going to end up doing the next loop. We're going to do another 7 and so on. And we'll end up building a 7x7 thing on the map. Alrighty, so now we just need to display our tiles as part of the snapshot system. In Waveform Collapse mod RS, add a new function as part of the implementation of Waveform Collapse Builder underneath Build. It's a member function because it needs access to the take snapshot command. I mean, it doesn't need to be underneath Build, by the way. I'm being very pedantic, but Rust doesn't care what order you put your functions and stuff in. But I think they were just trying to make it, again, I'm being pedantic. I think they were trying to make it clear where to put it. Like to make sure you get in the right impl block. We'll probably convert this from a reference to a vector to a slice. I bet Clippy's going to complain about it even. We'll see once we're using it, but change this to, yeah, it's already recommending it. It's not what I want. Okay, what did I break? Oh, I left this one here. So it's just more idiomatic Rust, so we'll do it that way. It is equivalent. Anytime you are bringing in a vector into a function, a reference to a vector, instead of doing ampersand vec and then the thing, you do ampersand, it looks like an array. It looks like a reference to an array. It is a slice. A nice thing you can do, by the way, with the slices is you can take like patterns is a vector. So you could take let test equal patterns 0 to 5. You could do that and actually, well, yeah, it's going to be, okay, that's not the right way to do it, is it? What is the syntax? I'm forgetting. I like how I'm going to demonstrate something and I mess up. Is splice as slice. We could just get the whole thing as slice. I thought we could do the range-based thing. We'll look at that in a bit. The thing is, you can do that. I'm messing up the syntax a little bit. Let's just keep going. But you can do that. You can actually take like a partial slice of it. Okay, so what we're gonna do in render tile gallery, we're gonna make a new map, set up a counter, an X and a Y. Well, the counter is less than the patterns.len, so each counter is going to be one pattern. I'm curious why we need to do it this way instead of some kind of iterator or something, so we'll find out. Now, you're not finding this. Render pattern to map. It does need to be public. Yeah, it does. Okay, so now we're happy there. So we're just gonna say render it, and then x plus equal chunk size plus 1. If x plus chunk size is greater than the map width. Move to next row. So then we move y. We increment y. But then we also need to check y. If y plus chunk size is greater than self.map.height, we're probably done. Move to the next page. Okay. All right, so pretty straightforward. We render the pattern. We check if we need to. So we then increment X, and if we need to, we go to the next row. But after we go to the next row, we have to also check to make sure that Y isn't going out of bounds. And if it is, we go to the next page, which that means we're doing this for each pattern. So a page is a pattern, right? No, a page is not a pattern, but we might have more. I think that's what it is. We might have more patterns than can fit on a single map. So we try to draw as much as we can on a map, and then if it doesn't work, we run out of room, we do another map. I think that's what we're saying by page. And we have to call it in build. So let's go up to build. There's our patterns there. Render tile gallery. And chunk size. Now notice that Ampersand patterns works. This is giving us a slice. This is the exact code that they use as well, but their code says to take a reference to a vector, ampersand vec tile type. So just to demonstrate, my code on this line is exactly the same, but that still works. I swear though, I thought I could do something like that. A reference to the slice. Yeah, no, that does work. I don't know what I did earlier. I don't know why I got mad earlier. I might have just made a dumb typo. In fact, let me try that one more time. Yeah, no, we're good. I think, did I leave the reference off earlier? Is that what it was? Yeah, I left the reference off. That's what it was. So now you see our type here is the ampersand vec. It looks a lot like an array, but what we're doing is we're getting only the first two things. We're getting 0 and 1, or we should be able to use the inclusive range to get the first 3 if we wanted to do it goofy like that. Whatever. So then it says also comments some code so it doesn't crash from not being able to find a starting point. They're doing they commented out this while stuff, but it was already commented out before. And they're still using this start index here, so we're good. If we cargo run, we should see the tile patterns from map sample 2. So let's take a look at it. I gotta click back in here. You gotta watch quick, because we're probably not gonna stay up very long. I'll run it a couple times so we get to see it. Oh, yeah, that did go very quick. There are 83 patterns. Very, very quick, but it was pretty cool to see. It'd be nice to slow that down a little bit or something. I could think of a really bootleg way to do it, to take a bunch of snapshots. I mean, we could just smush that in and get rid of it real quick. Just take like 10 snapshots and let's see a bit of a longer version here. And then we'll delete that. Some of those still went pretty quick. Let's move that to in here. Because we'll do it for each page. No, we're still just like skipping through those first ones. But I think we get an idea. We get the idea, right? So that's good enough. Let's take a look back over here now. And they've actually got screenshots for us too. We're almost halfway done. If you cargo run now, it'll show you the tile patterns from map sample 2. There we go. Notice how flipping has given us multiple variants of each tile. If we change the image loading code, by the way, so here's the example. So look at this one here. It has 3, right? And if we flip it vertically, it has 3, but it's now pointing down. This one here, that's pointing right, we flip it, it's now pointing left. And then I think this one that's pointing both ways, I think it's this one, but flipped twice. I might be wrong though. I think that might be how that got built. Or it was just another tile. And we have this one here, which again would be this, but flipped twice. Maybe. The 4-way. So if we change the image loading code to load demo 1 by changing the loader to that, we get chunks of our hand-drawn map. I don't think I'm going to do that right now. If that's what we're going to do, if that's what we want to use, then I'll change it, but I don't think we need to demo that. That's fine. It's not a hard change, but you know. So now, next up, we're going to build the constraints matrix. I'm going to take a quick break here for a couple minutes. We'll put on a song, and then I will be right back. And then we'll continue by building the constraints matrix, and should be the only break, so we'll keep going to the end. All right, we are back. So we're going to build the constraints matrix now. And before I even read it, I'm just going to go ahead and go out on a limb and say that's how we're actually defining which tiles can link up to which patterns can link up to which. So now we need to begin to tell the algorithm how it can place tiles next to one another. We could go for a simple what's next to it on the original image algorithm, but that would ignore a key factor in roguelike maps, connectivity. We're far more interested in the ability to go from point A to point B than we are in overall aesthetics. So we need to write a constraint builder that takes into account connectivity. We'll start by extending builder in mod.rs to call a hypothetical function we'll implement in a second. This is the mod.rs that we're working with for the wave function, not the other mod.rs. I think we have like 3 now, don't we? And it'll give us the signature of a new method, patterns to constraints, to add to constraints.rs. We're also going to need a new type and a helper function. We'll use these in other places, so we're going to add a new file to the waveform collapse folder, common.rs. Be enough to get us moving now. Let's do it. So where are we putting this here? Let patterns, render tiles, render tile gallery rather. Let constraints equal patterns to constraints and chunk size. So it's got to return something. We don't quite know what it is yet. In terms of like if we tried to auto complete that, it wouldn't know what to make it, but we got something because we're not using constraints in a way that can identify yet. So we need to also make common, and then we're going to go into mod.rs and do that. Just like so. And then we'll go into common. Use super tile type, derive, partial. What did I do wrong? Why are we not getting the completes? Okay, whatever. It's probably because I don't have the struct there yet. All right, so we're going to make this map chunk. And we're going to make a quick function. So this is basically map coordinate kind of stuff here. Tile, index, and chunk. Should look familiar. Y times the chunk size. That gets us our height, our Y value, basically. And plus X is just how far along in the row we are, right? Our X value. All that getting mushed into a single value, similar to what we've been doing with the map XY index, right? So let's look at map chunk. We have a pattern, which is a vector of tile types. Looks familiar to what we've been seeing already tonight. Exits. Well, we have up to 4 exits. So I guess we're assuming that exits are in the center of each tile, in the center of the chunk, up, down, left, and right. We could possibly have more. We could have them diagonally if we wanted. We could really define anything we want. So right now that's assuming that's building in a bit of limitation, but we could do something pretty interesting with that. And we're actually defining whether or not it even has exits. So I'm curious what a tile without exits would be used for, but sure. And compatible with. I'm guessing that is saying if we have a left exit, then we're compatible with something that has a right exit. No. Compatible with vec usize times 4. What are the vector of u sizes? I'm interested in that. We'll have to see how it works. Not yet sure. And I've already explained tile, index, and chunk. That's easy enough. Patterns to constraints. We're going to be adding that in here. Actually, I'll go ahead and read the tutorial because we're going to do that in a moment. Patterns. So we're defining map chunk to be a structure containing the actual pattern, a structure of exits, more on that in a moment, a bool to say we have any exits, and a structure called compatible with, more on that in a second too. We're also defining tile index and chunk, which is just like map XY index, but constrained to a small tile type. Now we'll write patterns to constraints and constraints.rs. Patterns to constraints. Chunk size I32. Back map chunk. Sure. Right. Now, this is a big old beefy boy, but doesn't look terrible. A lot of repetitive code, so I'll copy paste some of it. Move into the new constraints object. So let mute constraints is a vector of map chunks. I think we're going to return constraints. So that should make things happy. Now we're going to do this for loop for loop over all the patterns. We're going to copy this because we're going to do it again in just a moment. Except I should put the thing here first. Okay. So good. I broke that apart correctly. So we're assigning the pattern into the map chunk. We're making 4 vectors for exits, and I missed that actually. When we define map chunk, exits was a vector of bools. I'm intrigued to see how that's going to work. It's not exactly what I was thinking. It's an array of a vector of bools. Yeah, it's going to be interesting how we use that. Rather than just there's an exit or not. So something else is going to be going on. Has exits, we default to true, and compatible with is the same thing. An array of vectors, but these are U sizes, I believe. So after that, we, for exit in new chunk dot exits dot itermute. So we're obviously going to be modifying it for I, but we're underscoring it, so we're not using it. So we're going to loop from 0 to chunk size. And we're going to push false. So for each exit, we are going to have exits on like every tile. I see how we're doing it. So I think what's happening is we're going to loop over each border and determine if there are exits on the border. So there might be 3 or 4 different exits on the north border of the chunk. There might be 3 or 4, because all it takes is one tile to be an exit. But what if the whole side is empty? Then one of these vectors in exits is going to be north. Let's say it's the first one. Then all 7, assuming chunk size of 7, all 7 would be true. They would all be exits. Okay. I think I see. We'll confirm as we write it, but I think that's what's happening. So let mute number of exits, n exits equals 0. And then we're going to loop over the chunk size for x and 0 to chunk size. Yeah, check for north bound exits. Let north index equal tile idx in chunk. And we're going to fix y to 0. Because remember, this pattern that we have, we know, like, we have the borders and everything of the pattern. So it's going to be kind of easy to work with, fortunately. If new chunk dot pattern north idx equals tile type floor, now there's an assumption here though. We call it an exit, but that doesn't mean we can actually path through it. What I mean is, what if the entire, look at it this way. Imagine we had a chunk size of 4. Now imagine, don't do that. So what we have here is the inner part. I mean, this is an extreme example, but the inner part in this small chunk that I've drawn here are all walls, and the outer parts are all exits. So every single outer piece would be called an exit, but the inner part of the chunk is basically worthless. Now, there could even be a really bizarre case where, imagine it's wider, and we had like an opening in the middle like this, but then we were sandwiched in or something, and there's actually no exit, right? There could be some bizarre thing like that. So we're in the center here, and we well, no, that wouldn't quite work. You see what I'm trying to say, though? There may be exits, but that doesn't mean we can actually path to them if we were like stuck in the middle here. So I see some potential issues. You would have to make sure you define your tiles, your patterns in such a way that that can't happen, right? So you don't want to make any like empty areas, because then it could be possible that you would randomly generate your starting point in one of those empty areas that you can't path out of. Just already calling that out because I see it as a potential issue. So that's our northbound exits. Really easy. So guess what? South, west. I hate doing west before east, but that's what we got. There we go. So then we have to change up how we do this just a little bit. So for south index, it's going to be chunk size x chunk size -1. That's pretty straightforward because we're still looping over the x's, but we need to fix the y value to the south end of the chunk, right? Simple enough. And nothing else should change because we're getting the index and we just use the index. So not a big deal. Now for westbound exits, it's going to be chunk size as 0 and x. And then here it's going to be chunk size -1 and x. I think I covered those. So now we also need to update these. Now this is the part that's a little tricky. We're going in that order: north, south, west, and east. You have to make sure you maintain that order now. 0, 1, 2, and 3. Because we're probably going to be referencing that also for the compatible with, right? Maybe, I don't know. But it might be relevant, just a thought. So let me double check, because these are funky. Chunk size X and 0, chunk size X, chunk size -1, chunk size 0 and X, chunk size -1 and X. Yeah, that works. So the way this X value is working, we're not really going over the tiles of the chunk. What we're doing is, you can imagine in one iteration of this loop, or rather in one cycle of this loop, imagine again if chunk size is 7, what we're doing in the first step, we're checking 4 different spots, right? Although some of them may overlap in the first loop. I don't know, I'd have to math it out. But then in the second iteration, we're checking 4 different spots. In the third iteration, we're checking 4 different spots. So we're essentially crawling over all 4 sides of the chunk at the same time as we loop through this. And then we close that out, and we're down here now. If number of exits equals 0, new chunk dot has exits equal false. Oh my goodness. You ever miss home row and you start typing and you get some gibberish? Alrighty. Now, we're not done yet, because now we have to figure out what's compatible, right? So we're building a compatibility matrix. So we're cloning the constraints. We're going to mutably iterate over the original constraints. So we're keeping CH for now, which was the cloned. We're going to loop over the original constraints mutably. And now for J, potential in ch.iter.enumerate. If there are no exits at all, it's compatible. I find that interesting. So I guess what we're doing by there is we're saying we do allow tiles you can't traverse between. So if there are no exits, we just say, yeah, you can link up wherever. Go for it. Okay. So that's, I think, pretty straightforward so far. And compat is our map chunk. For compat in C, which is our map chunk, dot compatible with dot itermute. So we're looking at what it's compatible with, and then we just push in all those J's if there are no exits. And those are the, like, the indices, basically, right? I think that's how it's working. So we're doing this little match here just to literally like map between the different directions here, right? So if we're looking at north, then we care about their south, right? Again, we're matching up the tiles. So if I'm talking about an exit on my north, then the tile above me has to have one on their south, right? And that's how we're evaluating compatibility by direction. Let mute it fits equal false. Has any equal false. So we're going to iterate over the exit list, which again, we're getting out of our constraints, out of our map chunks exits, which we just populated up above. Remember this here. We figured out which tiles have exits. So we're going to loop over those exits. And we're getting the index, the slot, by enumerating it. And then we're just getting whether it's an exit or not, which is the can enter. If it can enter, has any equal true. If potential dot exits So then what we're doing is, again, we've built this opposite out, which we did right here with that match, right? So if we're on our north, then we need to check their south. So this is, again, where I set up here, exits 0, 1, 2, and 3 is important. That's what we're doing right here. We're indexing into that, and then we're checking the actual like index of the tile to see whether or not it's an exit. So if we can enter our tile, then if the potential tile, which is the other tile we're evaluating, if it has a matching exit or entrance, however you want to look at it, then we say it fits. I hope that makes sense because it's a little bit awkward, but it's actually, I don't think, too bad. If it fits, it sits. If it fits c.compatible with direction.push j, which is going to be similar to what we did up here, where we just like brute force did it for everything when we had the potential, when they had no exits. Which I still find interesting. I get it though. You could just have like a big wall somewhere and you say, oh yeah, that's cool. Yeah, let's go for it. If it doesn't have any, there's no exits on this side. We don't care what goes there. And that's it. So let's high level this because I think it's a little bit easier to think about in the high level. The way this compatibility stuff works, well, I mean, let's even back it up to here. And let me try to high level this. We're going to get the high level from the tutorial as well. So what we're doing is we're having to build out constraints. Remember, let's think about wave function collapse and let's think about that YouTube video I briefly pulled up. And we have a grid and we want to put sand down. When we put sand down, we define constraints that said sand can only go next to water or grass, right? Well, we're doing a bit of a more complicated version of that, where instead of saying sand and water and grass, we're saying we want to find where exits and entrances and stuff to tiles match up so we can actually path through the map. So we need to build out this compatibility matrix, right? We need to build out these constraints, and we're doing it dynamically. We're doing it in code. based on the patterns that we pull in. That way we can put any pattern we want, and it'll always be able to figure out whether or not it can build a map out of it. Or not whether it can build a map out of it, but it'll figure out how things link up. And then it can potentially build a map. So this is important. We start by building these constraints, which is just an empty vector initially. We loop through the patterns, and we take that pattern and turn it into a chunk. Basically, the chunk itself now owns that pattern. The exits and the compatible with and the has exits, we kind of default all that. But what we're really doing here is we're defining the north, south, west, and east exits. And what we see here is this X value is kind of crawling across each of those boundaries of the chunk. And if that's a floor, in other words, that means it's an exit to the chunk, from the chunk rather, then we mark that index. We mark that index as true. Well, I'm curious about one thing. Oh no, wait, right. We initialized it already. We did exit.push false. I'm wondering why we don't, probably because of the verbosity, but instead of vec new here, why didn't we do vec false chunk size expected as usize? Why did we do that? I mean, it's a little more verbose, but I don't know. It's probably more efficient to do that. But again, efficiency matters, but it's not as big of a deal on a one-time map generation, rather than something that's going to be running every frame. So anyway, we basically say, if our chunk size is 7, then that means we have 7 potential exits on the north, 7 on the south, 7 on the west, 7 on the east. So all we're doing is populating all these. We start them all to false, and then if it turns out that any tile that was a floor, we now set to true, because that's an exit. So then what we do is we do this for every single pattern, right? So we've now built this out for every single pattern, and that goes into our constraints. So now we need to build that compatibility matrix. So what we actually do is, what ends up happening with CH? Nothing? I feel like we cloned it and then just kind of threw it away, which I find interesting. Unless I missed something. I hope I didn't typo. I'm not seeing it. I'm just confirming. So anyway, now we know all the exits of every tile, and we've got them into these map chunks. We now want to find out what they're compatible with. And that's where it's important. So what we basically are doing is, oh no, CH is here. Yeah, I missed it. Okay, good. I wasn't seeing it. So we are using both. We're comparing both with each other. We're looping through the constraints here. And we're also looping through the constraints in the form of CH. So we have 2 copies and we're looping through, and it's basically like comparing every possible combination of constraints, right? Of map chunks, rather. And for every combination of map chunks, that's how I'm going to refer to this double for loop here. For each of these 2 combinations of map chunks, what's the way I'm trying to say it? For every possible 2 combination that we could have of map chunks, that's what these double for loops are. If there are no exits, and now this is where it's critical, C and potential, these are literally just 2 different map chunks. So C is the outer for loop and potential is the inner for loop. They're just 2 different map chunks. That's all we really have. So what we could think about here is C is our current, and then potential is the one we're comparing against, right? If either one of them has no exits, then we just go ahead and say, hey, they're compatible. And the way we're doing that is ch.iter.enumerate. Let me think. Oh, we're just pushing J. So we're saying it's compatible. Okay, yeah. So J is the index, the index of the chunk. That's critical. J is the index of the chunk itself. So then we're saying it's compatible with chunk J. So then later on, we can actually go back in and from constraints say, give me chunk J, whatever that is, and we know it's compatible with whatever C is, with whatever chunk C is, right? So that's the idea here, right? Well, where is compat is coming from C. Don't forget. Compat is coming from C. It's compatible with. There we are. Okay. So again, it's a little bit interesting, but we're saying so C is now compatible with like everything basically. That's how I'm reading it. Oh no. C is completely compatible with the potential with J. Yeah. Okay, there we go. C is compatible with J, and we just push that in there for all of the compatible with, which if we go back to here, compatible with was another one of those arrays of vectors. So then where that gets more interesting is down here where we have to populate it though. So let's take a look at that. We need to evaluate the compatibility by direction. Now, this is where the real meat, where the real magic is happening. Remember before, sand is compatible with water and grass. This is our sand plus water and grass. This is where we're really defining that. So what we do is we loop through the exits of our current. That's what the C is here. And direction is enumerated. So this is critical. C.exits.itermute. So we go back to common here. Exits is this array. 0 is north. The first vector is north. The second vector is south. The third is west. The fourth is east. So by enumerating that 0, 1, 2, and 3, north, south, west, and east. See, they happen to go in that exact order that I just said. That's the critical component here. That's kind of the meat of what we're doing here. If we're looking at our north, C's north, then we need potentials south, which would be 1. If we're looking at our south, 1, we need the potentials north, because we're talking about the bordering, right? We're talking about 2 of these patterns bordering each other. So then we have a couple just helper variables, it fits and has any. And now this is where we actually figure out how things line up. So we loop through the exit list, which is our C.exits, right? We loop through the exit list of our current. We're also enumerating it as slot. And then we just check if can enter, which was just the simple bool of the exit list. So if can enter, then we say has any is true. And then we also have to check against the potentials exits. So we have the slot here that we just got. This is where we're at on, let's pretend we're on the north wall here. And let's say we're on the 3rd slot. The index 3, 0, 1, 2, 3. Let's say we're, so it'd actually be the fourth. Let's say we're on index 3. So that would be our enumerated value. Slot would be 3. And we're on our north wall. So then we check the potentials south wall at index 3. And if they match, which we've already determined, the way these conditionals are going, if we made it here and then we made it here, like if we made it all the way in here, we know it matches, because if it can enter, and then if it's an exit, if it's true, then we say, hey, it fits. There's a match. That's the key. And then if it does fit, then we can go ahead and push that in to say it's compatible with. That's a lot. And then if it doesn't have any exits, then we don't care what goes there, so we can push it in anyway. Just do it anyway. Why not? Okay. I hope that means I said I was going to do it at a more high level, but I feel like I didn't quite. I feel like I went a bit low level. But again, I hope comparing it to the simple sand and grass and stuff, that's all we're doing here. We're basically building out that definition of sand and grass and connecting them like that, like I talked about earlier. But it's very beefy. But the cool thing about it is, again, we could put any patterns now and that works. So we're going to be in for some reading now. We'll get you a drink. We're going to be, let me take a sip of my water. This is a really big function, but clearly broken down into sections. Let's take the time to walk through what it actually does. 1, it accepts a first parameter. Patterns as vec tile type, the type we use to build our patterns. A second parameter, chunk size, is the same as we've used before. It returns a vector of the new map chunk type. A map chunk is a pattern, but with additional exit and compatibility information added to it. So we're promising that given a set of pattern graphics, we're going to add all the navigation information to it and return the patterns as a set of chunks. It makes a new vec of type map chunk called constraints. This is our result. We'll be adding to it and returning it to the caller at the end. Step 3, now we iterate every pattern in patterns, calling it P to save typing. For each pattern, 1, we make a new map chunk. The pattern field gets a copy of our pattern. Exits is an array, fixed size set, in this case of size 4, of vectors, so we insert 4 empty vectors into it. Compatible with is also an array of vectors, so we set those to new empty vectors. And we set has exits to true. We'll set that later. Step 2, we iterate from 0 to chunk size and add false into each exits field of the new map chunk. The exit structure represents 1 entry per possible direction, north, south, west, and east. So it needs 1 entry per size of the chunk to represent each possible exit tile in that direction. We'll check for actual connectivity later. For now, we just want placeholders for each direction. Step 3, we set in exits to 0 and make it mutable so we can add to it later. We'll be counting the total number of exits on the way through. 4, we iterate x from 0 to chunk size, and for each value of x, first, we check for northbound exits. These are always the location x0 within the chunk, so we calculate the tile index to check as tile index and chunk size x and 0. If that's a floor, then we add 1 to in exits and set new chunk.exits 0x to true. Then we do the same for southbound exits. They're always at the location x chunk size -1, so we calculate the chunk index to be tile index and chunk size x, chunk size -1. If that's a floor, we add 1 to n exits and set new chunks.exits 1x to true. We do the same again for westbound, which are at 0x, and again for eastbound, which are at chunk size -1 and 0. Shouldn't that be x? Hang on. Yeah, it's chunk size -1 and x. There is a typo there. Okay, so that was for each, we iterate x from 0 to chunk size, and for each value of x, we do all that. Then after that, If number of exits is 0, we set new chunk.has exits to 0 to false. There's no way in or out of this chunk. We push new chunk to the constraints result vector. Now it's time to build a compatibility matrix. The idea here is to match which tiles can be placed to which other tiles by matching exits on adjacent edges. Then, to avoid borrow checker issues, we take a copy of the existing constraints with let ch equal constraints.clone. Rust isn't a big fan of both reading from and writing to the same vector at once, so this avoids us having to dance around to keep it separated. For each constraint in our results vector, constraints named C, okay, so for each constraint, C, we iterate every constraint in CH, our copy of the constraints vector, as potential. We add an enumerator J to tell us how it's indexed. If neither C, the constraint we are editing, or potential, the constraint we're examining, has exits, then we make it compatible with everything. We do this to increase the chances of a map being successfully resolved and still featuring these tiles, otherwise they would never be chosen. To add compatibility with everything, we add J to the compatible with structure for all 4 directions, so C can't be placed next to potential in any next to potential in any direction. Otherwise, we iterate through all 4 exit directions on C, and to do that, we set opposite to the reciprocal of the direction we're evaluating, so north goes to south, east to west, etc. We set up 2 mutable variables, it fits and has any, and set both to false. We use these in the next steps. It fits means that there are 1 or more matching exits between C's exit tiles and potential's entry tiles. Has any means that C has any exit tiles at all in this direction. We distinguish between the two because if there are no exits in that direction, we don't care what the neighbor is. We can't affect it. If there are exits, then we only want to be compatible with tiles you can actually visit. We iterate C's exits, keeping both a slot, the tile number we're evaluating, and the value of the exit tile, which is can enter. You'll remember that we've set these to true if they are a floor and false to otherwise, so we're iterating possible exits. So first, if can enter is true, then we set has any to true. It has an exit in that direction. Then we check potential exits.exits opposite slot, that is matching exit on the other tile in the opposite direction to the way we're going. If there's a matchup, then you can go from tile C to tile potential in our current direction. That lets us set it fits to true. So if it fits is true, then there's a compatibility between the tiles, and we add J to C's compatible with vector for the current direction. If has any is false, then we don't care about adjacency in this direction, so we add J to the compatibility matrix for all directions, just like we did for a tile with no exits. After all that, finally, we return our constraints results vector. It's quite a complicated algorithm, so we don't really want to trust that I got it right. We'll verify exit detection by adjusting our tile gallery code to show exits. In build, we'll tweak the rendering order and what we're passing to render tile gallery. Okay, so in here, let patterns, good there, patterns to constraints, patterns and chunk size. Doing render tile gallery afterward. That threw me off. Oh, wait. Render tile gallery is now constraints. So self.map, chunk size, true, patterns, chunk size. Yeah. And what we're passing to render tile gallery. Good. And now this is going to be a vec of map chunk. So we can just do that right there. And things are going to be a little bit mad. We're also not calling this patterns, we're calling constraints. And render pattern to map also needs to be changed. Oh, wait. We're just passing in a map chunk. My bad. Okay, so that should make this happy now. I'll double check to make sure we're all good there. So then over here, past the map chunk, instead of pattern, are we renaming it to chunk? We are. And then map.tiles is no longer that, it's chunk.pattern.i, so we get access to the pattern. There's going to be some more work to do there, but let's scroll back up to this one real quick and just take a double check to make sure everything looks good. Render pattern to map, that is the same. And I don't think anything else changed. So we are good on that front. So now we're going to modify render pattern to map. And that means let's go back here. We're going to add some more work to this. And I'm going to copy these once I do the first one. So we're using downstairs again for easy access. So what are we doing? We're looping over the north exits and enumerating it. So we have X and northbound. If northbound is an exit, because remember, if it's true, it's an exit. So if northbound, dereference it. So basically we're saying if true, then we just get the index and we make it downstairs. Just as an easy way to see what the exits are with the downstairs symbols. So we'll go boom, 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 just like that. Southbound, westbound, and eastbound. But we're going to change this to 1. Whoa! Thank you for that follow. Scared me, that was loud. We're going to change this to 1, 2, and 3 here. And we need to modify what we're actually doing for the positions here. Because we can no longer just do start Y, right? We need to do start Y plus chunk size -1. And on the westbound, it's just start X. And then start Y plus X is I32. And then on this one down here, it's start X plus chunk size. Whoops. There we go. A lot of extra work there. But basically, simple idea. We did this in the Drunkard's Walk algorithm. We converted all the stuff that was being dug out on an iteration of the algorithm to downstairs as a very clear visual way of seeing what's happening. And now if I did this right, it runs and works, but that was a lot of typing. There could be an issue. Let's hope there's not. It's also going to go very quick though, so we just got to kind of watch. And okay, I see. Yeah, okay. It went very quick. I'm going to run it a couple of times. Take a look at those little patterns, especially the ones there at the end. You could see around the borders and stuff. You could see all the downstairs. It looks like it's working. Because the downstairs only seem to be appearing on the borders there. So yeah, I think it's good. I think we're good. Okay. That's, I mean, I can't really slow it down very effectively. That's the problem. But we don't have to worry too much about that. You know why? Because they were screenshotted for us. So now that we have the demo framework running, we can cargo run the project and see the tiles from the WFC demo 2.xp correctly highlighting the exits. And demo 1 exits are also highlighted. So that's great. Our exit finder is working correctly. I feel like this was exit 1, or demo 1. I feel like that's what we just saw. Maybe I never actually put it on demo 2. It doesn't matter. So that's great. Our exit finder is working correctly. So now we're going to build a solver. So remember, all we've done is build the constraints, right? So typically, anytime you start talking about building constraints, and we mentioned this earlier in the chapter here, it's just a solver. Wave function collapse is a really cool name because it's reminiscent of something like that, but it's really just a solver. What we've done is we've given constraints, and now we need to solve a problem. You can do that with other things. You could do that with like Sudoku, right? Sudoku essentially gives you a set of constraints at the beginning, which is the numbers that are given to you. Or if you're playing like killer Sudoku and you have the cages and stuff, those are also constraints. And using those constraints, you can then build a solver, or you can solve it yourself, right? That's what we're doing here. So now it's time to actually build the solver. You remember the old books of logic problems you used to be able to buy for long trips? Fred is a lawyer, Mary's a doctor, and Jim is unemployed. Fred can't sit next to unemployed people because he's snooty. Mary likes everyone. How should you arrange their seating? This is an example of the type of constrained problem a solver is designed to help with. Building our map is no different. We're reading the constraints matrix, which we built above, to determine which tiles we can place in any given area. Because it's a roguelike and we want something different each time, we want to inject some randomness and get a different but valid map every time. So let's extend our build function to call a hypothetical solver. Righty? Let's do that. Down in here. And where do we want to put that? Right after the render. So we'll do it here. And we'll say self.map equal map new self.depth. And then using that, we'll build a loop. And I guess we're going to loop until we get a valid one. So let mute solver equals solver new constraints dot clone chunk size and self dot map. All right. We should put that actually. Okay, give me that comment. Give me just the comment. So we obviously don't have a solver yet. We didn't make one, but this is straightforward enough, right? We make a solver based on our constraints and the chunk size and the map. And we, while not solver.iteration, take a snapshot. Interesting phrasing there, but I guess we just keep iterating through the steps of the solver. And then eventually it'll stop iterating. So that's probably each step of the solver is going to be another tile on the map, I would imagine. And then we take a snapshot, and maybe we started out with a bad tile and we just picked some bad randomness, and we got to a spot at the end where we could no longer iterate, where we could no longer add tiles, right? Add chunks to the map. It's like, oh man, you know, we got to the corner here and we just can't fill it in because nothing matches our constraints. That would be an example of an impossible condition. So if solver.possible, we break, otherwise we do it all over again. I mean, that's about it. Now, I'm noticing that we are making the map before we go in here. I do find that interesting. Do we not want to make a new map every time to repopulate it with fresh walls, or is that unnecessary? It may be unnecessary. It depends on how we write solver. If we write solver and just assume we don't care anything about the map, and then yeah, we'll see. We'll see. So let's go ahead and pop back over then. Make a freshly solid map since we've been using it for rendering tile demos and don't want to pollute the final map with a demo gallery. Yeah, see, we might need to keep that in mind. And then we loop the Rust loop that runs forever until something calls break. Inside that loop, we create a solver for a copy of the constraints matrix. We copy it in case we have to go through it repeatedly. Otherwise, we'd have to move it in and move it out again. We repeatedly call the solver's iteration function, taking a snapshot each time, until it reports that it is done. If the solver gave up and said it wasn't possible, we try again. Question, is it really necessary that we clone the constraints rather than just give a reference? Well, that does create issues. Yeah, it does create issues, because if we give a reference to the constraints, I think we start running into some lifetime-ish. I might be wrong. I'm thinking about it for a moment, but I think we might have a bit of a lifetime issue where, let's see, because we would use that solver and then we would kind of rebuild a new solver with a reference to, I don't know if that would really be a problem or not. I don't think it necessarily would, because we're building the solver in the loop. So every time we go through, it's going to be a new solver. We'd be losing that reference. And it's not even a mutable. Well, I don't know. It might be. We might be mutating it somewhere. I wouldn't think so. Anyway, though, let's continue. We'll see how it works. So we make a copy of the constraints. We repeatedly call the solver's iteration function, taking a snapshot each time until it reports that it is done. If the solver gave up and said it wasn't possible, we try again. We'll start by adding solver.rs to our waveform collapse directory. I'm going to go ahead and do that. You don't need to see me add a file. And I'm going to do what I did before and do mod solver and use solver everything. And I'm just going to move over into the solver file, and then I'll be there when we get back. So we'll start by adding solver. It needs to keep its own state. That is, as it iterates through, it needs to know how far it has come. We'll support this by making solver into a struct. So now let's hop over and let's make the solver. We'll do map chunk. Chunk size, I32. So we have option, which is a vector of optional U sizes. So remaining is going to be index and number of neighbors. Okay. Oh, okay. I understand, I think. It's a vector, so it's probably going to be for every chunk, I believe. Okay, and we don't have a new yet for obvious reasons. Let's click back over. So this stores the constraints we've been building. The chunk size, we're using the chunk size we're using, the chunks we're resolving, more on that in a second, the number of chunks it can fit onto the target map, chunks X and chunks Y, a remaining vector, more on that too, and a possible indicator to indicate whether or not it gave up. Chunks is a vector of option usize. The usize value is the index of the chunk. It's an option because we may not have filled it in yet. So it might be none or some. That nicely this nicely represents the quantum waveform collapse nature of the problem. It either exists or it doesn't, and we don't know until we look at it. Remaining is a vector of all the chunks with their index. It's a tuple. We store the chunk index in the first entry and the number of existing neighbors in the second. We'll use that to help decide which chunk to fill in next and remove it from the remaining list when we've added one. We'll need to implement methods for solver too. New is a basic constructor. So yeah, remaining is a vector of all the chunks with their index. We store the chunk index in the first entry and the number of existing neighbors in the second. We use it to help decide which chunk to fill in next and remove it. Okay, so we're probably gonna use maybe like a filter, a sort. I don't know, we might sort by the number of neighbors or something. I'm not sure. The example in on the video I mentioned at the start, they talked about how you usually want to pick one whose domain has already been narrowed down a bit. So you'll kind of start in one area of the map and build from that area rather than going to completely different spots of the map. You want to build out from somewhere, kind of. That's roughly speaking. Go and watch the video if you're interested in that. So, impulse solver. Get mad at me, come on. Okay, so constraints. Just do that. Damn it. I messed up. It's fine though. So we build out a vec of none. That's easy enough. Chunks X and Y. We're going to calculate those in a moment. Remaining, we're going to calculate. Possible is going to be true for now. And let's go ahead and do some quick calculations. Let's bring in map. Should not be yeah, there we go. Like, I don't know why you're not giving me the right import. I didn't think it was, at least. Okay, now we need to calculate a couple things here. Chunks Y with height. Easy enough. Literally just dividing the map size by the chunk size. We'll build a new vec for remaining. And then we'll just loop over like how many chunks we have. And we'll push that index in along with saying, for now, 0 neighbors, because we haven't done anything yet. And that should be enough to get us going for now. Still got more to do. We need the iteration, and we're going to need a couple helper functions. So take a look here. So this calculates the size for chunks X and chunks Y. It fills remaining with every tile and no neighbors, and chunks is filled with none values. It sets us up for our solving run. We also need a helper function called chunk index, or chunk IDX. All right, and there we go. Simple enough. This is same thing we've been doing before with maps. We just did it earlier as well. Converting indices, not difficult anymore. I mean, never really was. What I always say is if it seems confusing, draw out a 2D grid, like a 2D array, draw like a 5x5 or something, and do the math yourself. Figure out, look at how it works. That's the best way I can explain that. It's not that bad though, basically, because this just tells you what row you're in, and this tells you what column you're in. All right, so now it's a lot like XY index and map, or tile index and chunk in common, but it's constrained by the number of chunks we can fit onto the map. We'll also rely on count neighbors. So this is a big beefy boy. Chunk Y, or chunky. So if chunk X is greater than 0, then let left index left index is the chunk index for chunk X minus 1 and chunk Y. We're going to match on chunks and then get that from that index. And our none is going to be nothing. Our sum is going to be plus equal 1. We're just incrementing that because that is, we're just counting neighbors. Simple, right? So now, what did I do wrong? Expected I-32. Why did you expect it? What am I doing? Yeah, no, we don't. Hold on, I feel like I'm doing something stupid. That should be pretty straightforward. Match self.chunks dot, or not dot, but left index. And that gives us the option, so we match on the option. Neighbors is an I-32. Let's see, what? What am I doing there? Expected I-32 because of, oh. Oh. Oops. Baby, come back. You can blame it all on me. I lost my terminal. It's only mad because it thinks I'm like returning stuff and all that right now, doesn't it? We need to return neighbors later on. So let's just go ahead and do that. I think, yeah. All right, I was getting overzealous. Now we need couple more of these. And this is the fun part, making sure you don't typo these when you got very similar things. If chunk x is less than self.chunks x minus 1. I got you on that drink redeem. Appreciate it. We got that right index. And we're going to need to do chunk x plus 1 and chunky. We'll match on the right index there, and all that is good. Now, if chunk y is greater than 0, then we're going to make the up index. And this is going to end up being chunk x and chunk y minus 1. And if chunk y is less than self.chunks y minus 1, and we're going to do chunk x and chunky plus 1. And we need down index. Almost missed that. I mean, it doesn't really matter. The names are consistent, but it would be a little confusing. And we return neighbors. So a little bit beefy because of the way we're having to check against chunks. I've done something like this before when I did a Conway's Game of Life in a chunked world that I could just keep generating infinitely, or, you know, you always got to be pedantic with that. Of course, it's not infinite. You'll run out of memory and stuff one day. You'll run, even if you're caching it to your disk, you'll run out of drive space one day. You know what I mean, though. Comparing chunks is a little bit annoying sometimes. You can obfuscate a little bit of that, and that's kind of what we're doing here, because now we can just ask for count neighbors. We had to do this stuff only really one time, but it's just a way to figure out how many active chunks do we have, right? And remember, we populate that vector with options, so that's why we're able to do just a quick match here on none or some. We don't even care what's in there. All we care is that something is there because we've populated the chunk. So it's very easy, very simple, not much to it there. I like it. And yeah, there is a good note here as well, though, that it could be smaller. This function could be a lot smaller, but I've left it spelling out every step for clarity. It looks at a chunk and determines if it has a created, not set to none, chunk to the north, south, east, and west. Finally, we get to the iteration function, which does the hard work. So let's take a look at this big old beefy boy. So it's a public function iteration, and it just returns a Boolean. Now, can I get you to fill in the types for me? No. If I went back to the other file, I could, but I don't feel like doing that. All right, and it's going to return a Boolean somewhere down the line. It is a big old beefy boy. We're just going to return false here at the end. That's going to be our fallback case. So we're going to have early returns for true. So that's the first thing to think about, is just make sure this thing's not yelling at us the whole time we're in here. Okay. So now let's get this is a really, really big old beefy boy, okay? This is going to take a minute. If self.remaining.is empty, then return true. All right, we're done. Of course, that's not correct. We're going to populate the neighbor count of the remaining list. I'll recount what's going on here when I'm done with this block, with this loop. All right, let's break this down. Remember, I am learning this at the same time too. I understand the general idea of the algorithm, all that. I gave a high level overview of the algorithm before we started, and but I'm still learning as we go as well. So I like to take time to break these things down for my own benefit as well. And it's good. It's good to exercise that, to be able to look at code and try to figure out what's going on, right? So we're obviously we have a very helpful comment there. Populate the neighbor count of the remaining list. So it looks like we're gonna do that for all the remaining. So we'll see how that works. So we're gonna take a copy, which we're gonna do by cloning rather. So self.remaining.clone, we're gonna get a copy of the remaining, and then we're going to basically just default saying there are no neighbors. So neighbors exist is false. And then we're gonna iterate through remain copy, itermute in fact. And then for each remaining in there, for each R, we're going to get the index, which is r.0, and we're going to calculate our chunk x and y, and then we're going to get the neighbor count with that count neighbors we just got done making. If the neighbor count's greater than 0, then we have neighbors, so neighbors exist can be true. And then we simply modify r to, like, we still give it the same index as before, but now we update its neighbor count to what we just found. That's all there is to it. So next up, remain copy, sort by, and I believe I mentioned this a few minutes ago that we're probably going to end up sorting or something to figure out basically who has the most or least neighbors. And that's basically what we're doing here, it looks like. Self.remaining equal remain copy. So what we're doing is, once we've made that copy, we count all the neighbors, we sort it by the neighbors, which is B.1 and A.1, and then we slide that back into self.remaining. Here we go. Now, pick a random chunk we haven't dealt with yet and get its index and remove from remaining list. Let remaining index equal if not neighbors exist. We're gonna do RNG roll dice. It's gonna be a 1D self.remaining len as I32 minus 1. Gonna make sure we don't go out of bounds. Else 0 usize. Yeah, so if it has neighbors, we do that random roll, or no, if it doesn't have neighbors, we do that random roll, otherwise 0. Wait, no, I'm sorry, I said it wrong. Let remaining index equal if there are no neighbors, yeah, that's weird. I think I need a moment to wrap my brain. Something about that is just weird to me right now. I get that we're getting an index. I'm not 100% sure about the neighbor check right now. And why we say 0. 0 would just be the first index. Just get the first thing. I guess that's the idea. But we've already sorted it. Remember, we did sort it already. So that already implies that we're getting one with the... Let's see, if it's B1 compared to A1, then we're going in descending order? I think we are. Okay. I think we'd be going in descending order. So we're getting the ones with the most neighbor. When we say 0 is our remaining index, that should be the one of the ones with the most neighbors. So then we'll pick a random chunk we haven't dealt with yet and get its index removed from the remaining list. So that part's pretty self-explanatory. We get the chunk index and then we do self-remaining remove. Okay. Sorry for the little delay there. I mean, I got to break down what I'm doing as I'm doing it. I got to make sure I at least have an understanding of it. It's how you learn. All right, so we'll get our chunks X and Y. I got you on that hydrate as well. Appreciate that. I have been talking a bit. All right, so chunk X and Y, we just did that a little bit earlier, same method. We mod and divide. We've seen that a few times, not going to go into all of it. How you doing, by the way? Hope you're doing all right. Thank you again for the follow. I appreciate it. All right, so we're just setting up our options as empty vec. Don't really care yet. A vector of U sizes. If chunk X is greater than 0, let left index equals self.chunk index chunk X minus 1 and chunky chunk Y. Now we're going to have to do this for... It's going to be very similar to what we've already done, in fact. But we're doing extra comparisons, so we can't exactly just use the existing code 100%. We could extract some of this out and make it a little bit cleaner, though. But we're not going to bother with that right now. We're going to keep going. But you should recognize this, right? The neighbors, chunk X greater than 0, we're doing a left index. Very similar, right? All right, we do got to break down what's going on with the 3 here. And the 2 and the 1 and the 0. These should be the borders that we've already talked about. So let's keep this. So left index, then we do right index, and we do up index, we do down index. We'll get those in place first. Then we need our conditions here. Try and do these in order. Okay. So now, right index is going to be chunk x plus 1, chunky. And then, very important, this needs to be a 2. Nothing else should need to change. This should be a 1, and this one should be a 0. And then this will be chunk x on both of these. And then chunk y minus 1 and chunk y plus 1. And I really hope I didn't miss something there. So let's break down what these are doing before we continue. It's very similar. So we are calculating the neighbors again here, but we're also pushing in potential like matches, right? We're pushing in matches, compatibilities. So what we're basically saying is which indices of our constraints is this thing compatible with, right? And that's going to also be based on the side of the chunk. So the left index is west. So then let me put it here. 0 is north, 1 is south, 2 is west, 3 is east. So if our left side would be west, then we need to find out compatible with east, right? 3. Vice versa. If we're on the right, we need to find out what's compatible with on the west. So, because again, we're matching against a different chunk. So our right matches with their left. So that's what these 3, 2, 1, and 0 are as we're going through the up, down, left, right indices here. It's a little weird, but hopefully it makes sense. So next, we've calculated the neighbors and we've pushed in options, which are basically just saying this is what could possibly be a match to our current chunk, right? So now if neighbors is 0, nothing nearby, so we can have anything. We're going to roll dice. We're going to do a 1 self dot constraints dot len, and I'm going to guess we're going to do as I32 and then a -1 as u size. So that's now an index. Basically, we just need to get a random thing from our constraints. So then we're going to say self.chunks chunk index will sum new chunk index. Now remember, the self.chunks, the self is our solver, right? So we're now saying the chunk at this index is whatever this new index is, and this new chunk index comes from our constraints. So left x is chunk x times chunk size. We're going to do right x, which is basically the same thing, but we're adding 1 to chunk x. Top y, chunky, as I32 times self.chunk size as I32, and bottom y is chunky. I actually did type it. as I32 plus 1 times self.chunk size as I32. All right, just get our boundaries here for where we're going to be doing this. Let mute I u size equals 0, not 9, 0 for y and top y to bottom y, or x in left x to right x. Let map idx equal map.xy index with the x and the y there. Let tile equal self.constraints new chunk index dot pattern I. We're going to set this to tile and I plus equal 1. Now that's a lot. So let's see what is happening here. I don't think it's actually too bad though. What we're doing is, as we said, we get a random, if there are no neighbors, right, we can just pick whatever. So we get a random chunk. We literally just do a roll throughout the possible indices from our constraints, which are just different map chunks. Remember, a vector of map chunks. So we go through those. We pick a random one. We're happy. So then we set this within our solver. So our solver, it's now a sum. So our solver knows that we have something there. And then we do the left, right, top, and bottom values, right? We calculate, it's basically a bounding box. And remember, this is based on chunk size, right? So now, using these values, we can loop through them to get XY values, and we can convert them to map indices. But we also have this I value, and this I value is going to let us loop through our pattern as well. So that's going to have the effect of each time we go through the pattern, we're going to map whatever tile is in our pattern to that XY index here. And that's what we're doing here. We're setting the map tile to whatever was in our pattern. Then we increment I. So remember, the key is it's a 1D vector. It's not a vector of vectors. It's just a single vector that we're treating as a 2D vector. So we can just go through the whole thing, but this map index and the way we calculate the top Y, bottom Y, left X, and right X, that's going to give us the 3D, or not 3D, it's going to give us the 2D approach. That's going to give us different rows. So we're just going to read, and it's going to have the effect of grabbing the first row, grabbing the second row, grabbing the third row, and stuff in order. Very critical, but also I think hopefully not too bad. But we're not done. We need an else clause, right? So if there are neighbors, now this is where it's going to get a little bit more interesting, because we're going to have to really take into account the constraints. There are neighbors. So we try to be compatible with them. So we're going to make options to check is a hash set of U sizes. So usually those are going to be indices. That's what we're usually using U sizes for, some kind of index. We'll see how it works. That's my guess. We're going to iterate through the options that we built up earlier. Now remember, options is basically saying the valid constraints, right? Yeah, the like constraints dot compatible with. So let's see, where are we at? So we're going to loop through the options for I in O.iter, because that is now also a vector. So we're going to get the indices out of here. Options to check dot insert star I. And why are you mad? Oh, we didn't actually import you. I was like, why didn't we get insert? That's why. We didn't import it. Okay. So we're basically just adding all those into this options to check. But hash set's going to get rid of duplicates, so that's nice. Then let mute possible options vac usize equal vac new for new chunk index in options to check dot iter. Like I said, those are going to be indices, so we did confirm that here. Call it new chunk index. For new chunk index and options to check dot iter, we're going to assume true for now that it is possible hold on. Yeah, there we go. It's a big old beefy boy. We're not done. We got a lot more to do, but let's break this down. Possible options. So we loop through the options to check, and then we loop through options, which came from, see, I don't even remember where they came. Oh, okay, that's what we populated earlier. So we loop through options, and we want to make sure that if an option does not contain the new chunk index, then it's not possible. We just say no. But if it is still possible, if it does contain that chunk index, then we push that into our possible options. So that's the first part of like actually checking against things to make sure we're good. Then, if possible options dot is empty, oh no, it's not possible. We log that. Self.possible is false. Return true. Else, if there are possible options, then let new chunk index equal if possible options dot len equals 1, 0. So we're not doing a random roll. Else rng.roll dice 1d possible options.len as I32 minus 1. So basically, if there's only one thing here, we don't need to calculate an index. We'll just say 0. Otherwise, we do a roll. We actually are almost done now, though, because this is a big old beefy boy. I'm going to run through this whole thing, and we're going to break it down again myself. Then we're going to read the description for the tutorial and get their explanation. So we're going to like double down on this thing. We're going to make sure we try to walk away with some good understanding of how this solver works. I want to reiterate that before, because I know it's like, oh, there's so many things happening. You know what? I'm not doing that again. Let's see, chunk x as I32 times self.chunk size is I32. Right x, chunk x is I32 plus 1. Self.chunk size is I32. Yep. Chunk y times chunk size chunk y plus 1 times chunk size. We're good. All right. See, I didn't want to do that again. How much? It's just saved minutes. Not really, but feels like it. Been going over 3 hours, and there's still a good chunk, no pun intended, of this session to go. I knew this was going to be a long one. This is the longest chapter so far. I don't know if anything's going to match this one, but this is a big old beefy chapter. You know what? This is probably going to be pretty much identical to this. So I will compare and contrast rather than retype the whole thing. So for y and top y to bottom y, for x and left x to right x, let map index equal map.xy index xy, let tile equal self.constraints, new chunk index is usize dot pattern I, map tiles, map index equal tile, and I plus equal 1. Boom, 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 boom. We go all the way through, and we say false. So false, to me, is actually the indication that we are not done, and true is the indication that we are done. If there are no possible options, it seems to be. And also self.possible. Is there another place that we return up here, right? At the very top. If self.remaining is empty. Okay. So what this is, let's break this down at a high level first of all. This is an iteration. What we're actually doing here, this structure maintains a state. It keeps track of a bunch of stuff from one iteration to the next. So we're not building out like an iterator, but every time we go through, we're basically calculating some new data based on the current state. And we return the state whether we are done or not in the state of the in this Boolean here, right? So we say if we return true, we're done. It's either empty or we ran out of possibilities. And if we ran out of possibilities, then we also set a variable to say it's not possible. Self.possible is false. But if we get all the way through, we return true, and self.possible is still true, then it's actually a completed solvable map. Like it's a solved map. That's the first like high level thing here. That's kind of how we're using it as an iterator. What we return tells us if there's still work to be done. And then we have a variable that also tells us the state of like, did it succeed or not, right? So we basically are, every time we go through, and this is what's critical, we're not like doing the entire thing in this function. We're not like wrapping this in a loop. We're doing all this one time, every time it's called. And it's like a new iteration. So we go in, and that's why we sort this. So we're basically populating the neighbor count of the remaining list, and we're sorting them. And then we get a neighbor from that sorted list, either from a roll or just with 0 here, with our index 0, if there are neighbors. Which again, that part's a little bit confusing. Hopefully we break that down more. I think I get what's happening, but that part's throwing me off a tiny bit. Basically, it says if neighbors don't exist, do a random roll throughout all the remaining. If neighbors do exist, your index is 0. And then we say, I think what it is, so I think we talked about this before, where you want to pick things that are already kind of in areas that are somewhat populated, because those have basically reduced the domain space of possible options. And I think that's why we're doing that. Otherwise, if there are no neighbors, then we pick the first thing in the list, which we know is going to have 4 neighbors. So yeah, so because we already like removed a thing from remaining that we've just processed. Okay. So anyway, after that, what do we do? Chunk index. We do chunk X and Y. We get the neighbors, and we're figuring out the options, which I don't like the int here because that's not a meaningful variable name. But all we're basically doing here at the high level is this options. We're saying compatible with are the different possible chunks, the different possible constraints, if you will, the different map chunk structs that we have by index. Remember, this compatible with, it's a vector of u sizes, right? And this 3 here is, was it west or east? I wrote it down earlier. I don't remember. It's east or west. This is east or west. And then 1 and 0 are north and south. So basically we're saying if we're on the up index, I need to know what's compatible with this here, right? If we're on the down index, if we're on the lower half, I need to know about the compatible with like the upper half of the other tiles, right? That's basically all we're doing. We're getting all the possible options of chunks that are compatible with the chunk that we're currently on. If there are no neighbors, then we could just kind of put whatever we want. And when we say are no neighbors, what we really mean is we haven't populated those neighbors yet. No, none of them have been populated. So the domain space of possible options is anything we want it to be. So then at that point, we just randomly pick one and we slap it into the map. And that's what this bit is here. We loop over the pattern and we apply the tiles to our map. Otherwise, there are neighbors, so we have to check compatibility with them. So then we actually go through and basically build out our possible options. So we build out this options to check thing here, which is a set to make sure we don't duplicate. That's I guess a big part of it is to make sure we don't duplicate the potential options. We're kind of flattening things down a bit. Let mute possible options. We then check to make sure that they actually contain the same chunk index. And if they do, then that goes into our list of possible options. If we have no possible options, well, that's a failed solution. We throw it away, we return true to say we're done iterating, and we set possible to false. And that's something we checked back in the calling function in build. Otherwise, if there are possible options, we go through and we pick one. Either the only one, if there's only one in the list, we get that one, or we randomly pick one. Then, once we've picked it, we basically draw it to the map with the same kind of code as earlier. We do the left, right, top, bottom, we loop through it, we add them to the map, boom, that's it. I told you, that is a big old beefy boy, right? That is a big one. So let's read their example. And I'm going to take me another drink real quick. Let's read their explanation. This is another really big function, but once again, that's because I tried to keep it easy to read. Let's walk through the algorithm. If there's nothing left in remaining, we return that we have completed the map. Possible is true because we actually finished the problem. We take a clone of remaining to avoid borrow checker issues. We iterate our copy of remaining, and for each remaining chunk, we determine its X and Y location from the chunk index, call count neighbors to determine how many, if any, neighboring chunks have been resolved. If any neighbors were found, we set neighbors exist to true, telling the algorithm that it has run at least once. And we update the copy of the remaining list to include the same index as before and the new neighbor count. We sort our copy of remaining by the number of neighbors descending, so the chunk with the most neighbors is first. Let me double check one thing here. Oh, right. That... right? Oh no, this is where we remove. Okay. This is fine. I had a doubt. So we sort our copy by the number of neighbors descending. I did say that correctly earlier. So the chunk with the most neighbors is first. We copy our clone of remaining back to our actual remaining list. We want to create a new variable, remaining index, to indicate which chunk we're going to work on and where it is in the remaining vector. If we haven't made any tiles yet, we pick our starting point at random. Otherwise, we pick the first entry in the remaining list, which will be the one with the most neighbors. And that's the trick with the, yeah, if we haven't made any tiles yet, there will be no neighbors. That's the trick on what I was getting stumped on a little bit earlier. We obtain chunk index from the remaining list at the selected index and remove that chunk from the list. Now we calculate chunk x and y to tell us where it is on the new map. We set a mutable variable neighbors to 0. We'll be counting neighbors again. We create a mutable variable called options. It has the rather strange type vec usize. It's a vector of vectors, each of which contains an array index usize. We'll be storing compatible options for each direction in here. So we need the outer vector for all directions and the inner vector for options. These index the constraints vector. If it isn't the leftmost chunk on the map, it may have a chunk to the west, so we calculate the index of that chunk. If a chunk to the west exists, isn't none, then we add its eastbound compatible with list to our options vector. We increment neighbors to indicate that we found a neighbor. We repeat for the east. If it isn't the rightmost chunk on the map, we increment neighbors to indicate that we found a neighbor. We repeat for the south and the north. If there are no neighbors, we find a random tile from constraints. Figure out the bounds of where we're placing the tile in left X, right X, top Y, and bottom Y, and we copy the selected tile to the map. If there are neighbors, we insert all of the options from each direction into a hash set. We used hash set to de-duplicate our tiles earlier, and this is what we're doing here. We're removing all duplicate options so we don't evaluate them repeatedly. We make a new vector called possible options for each option in the hash set. Set a mutable variable called possible to true, and check each direction's options. If it is compatible with its neighbors' preferences, add it to possible options. If possible options is empty, then we've hit a brick wall, and we can't add any more tiles. We set possible to false in the parent structure and bail out. Otherwise, we pick a random entry from possible options and draw it to the map. So while it's a long function, it isn't really a complicated one. It looks for possible combinations for each iteration and tries to apply them, giving up and returning failure if it can't find one. The caller's already taking snapshots of each iteration, so if we cargo run with our wfc test1.xp, we get something like this. A little bit of a spoiler alert a minute ago. I didn't really pay attention, but whatever, we're good, right? Which one are we even using? Image loader. Load Rex map. Where are we using it? We're using demo 1. Okay. Let's cargo run this bad boy. Fingers crossed, right? I do not want to debug that right now. I think I broke something. It's kind of building something. I mean, we got something that worked, but that did not look right. So unfortunately, I do have to debug a little bit. And this is the one problem I have with this section so far is there's a lot, and I understand why, but there is a lot that you do between running, and that leads to potential issues, right? So I need to go take a look at some of my solver stuff here and give me a couple minutes while I just double check everything here. I'll kind of think out loud a little bit, talk out loud a little bit, but it's not going to be very helpful. I do apologize. So what do we have here? Y times self.chunks x plus x as u size. That's good. Count neighbors. This is what I'm tempted to even just copy at this point. Left index, self.chunk index, chunk x minus 1, chunk y. And we do that left index there. Cool. Let's see. Neighbors plus equal 1, yep. So chunk x less than self.chunks x minus 1. Then it's a right index. It's chunk x plus 1 and chunk y. And we use right index, neighbors plus 1, plus equal 1. Chunk y greater than 0. Up index, self.chunk index, chunk x, chunk y minus 1. Up index, good. And then chunk y less than self.chunks y minus 1, chunk x, and chunk y plus 1. We're using down index on both of those. Perfect. So next up, we get to the iteration. That's where I would assume there might be a problem, because that did not look like the right generation there. So let mute remain copy. We clone that. Neighbors exist as false. For r in remain copy dot iter mute, index equal r dot 0. Chunk x is idx mod self dot chunks x. Chunk y is idx divided by self dot chunks dot, or self dot chunks x. That's still good. Let neighbor count equal self dot count neighbors chunk x and chunk y. Let's see. Hold on. Let neighbor count neighbors chunk x chunk y. If neighbor count is greater than 0. Oh no, that's right. Neighbors exist equal true. And then star r equal r dot 0 and neighbor count. We're good there. Now we sort by, we do remain copy AB, and we do B dot 1 dot compare to A dot 1. That's good. And self dot remaining is remain copy. Okay. Let remaining index. Well, if no neighbors exist, roll dice 1 to self remaining len as I32 minus 1. 0 u size as the else. Chunk index, self remaining index dot 0, self remaining dot remove remaining index. Okay. Let chunk x is chunk index mod self dot chunks x. Chunk y is chunk index divided by self dot chunks x. I was hoping I was gonna have done the dumb thing there and said like chunks y or something. I did not, so we got to keep going. Hold on, I dropped something. Okay, no, I got it. If chunk x is greater than 0, left index, chunk index, x minus 1 and y, we do left index. Now the compatibility stuff could be wrong somewhere. So neighbors plus equal 1. Options.push self constraints in T compatible with 3. If chunk x is less than self.chunks x minus 1. Chunks x minus 1, yeah. Then we have a right index. And it's chunk x plus 1 and chunk y. Perfect. Match on right index. And it's compatible with 2. That seems fine to me. If chunk y is greater than 0, then it's chunk x and chunk y minus 1. With up index, we match on up index. Constraints, compatible with 1, okay? If chunk y is less than self.chunks y minus 1, let down index equal this here, chunk x, chunk y plus 1. And we match on down index. And we use 0 for compatible with. I think that's fine. If neighbors double equals 0, there's nothing nearby. So we do new chunk index, we roll dice, constraints.len as I32 minus 1. Self.chunks, chunk index, left x. Chunk x is I32 times chunk size, chunk x plus 1. I mean, all this is looking fine. Let me take, just for posterity. Maybe I'm just being too harsh on something. Hang on. We could try something different. Let's try something different before I keep going there, because that's not produced anything useful yet. I felt like I was pretty careful. Let's try demo 2. And let's see if this tiles correctly. Because this one's pretty simple. It is not really tiling correctly. No. You know what that gives me an indication of is that it could be our constraint stuff. I'll continue, or like it could be our solver. It could also be an issue with the way the exits were done. Actually, it's possible to have things that don't connect. When I'm looking at it, and let's take a look here, and they even mention it. So on the first one, not the greatest map, but you can watch the solver chug along, placing tiles one at a time. Now we'll try it with this one here, and there are tiles that don't really connect well. And it says this is kind of fun. It lays out like a jigsaw and eventually gets a map. It isn't well connected as well connected as one might hope. The edges with no exit lead to a smaller play area, which is called at the end, but it's still a good start. So we can do something like this. But I'm curious, like, I feel like this is even more well-formed than what I was getting, wasn't it? Let's try it again with demo. Actually, no, let's leave it as demo 2 so I don't have to recompile. And let's take another look at it. I mean, they are linking, some usually. It's not perfect, but that was a terrible map. It's pretty cool though because it's still like a working map. The worst part about it is that it's a lot to go through, like I was saying already. It's a whole lot to go through. And I don't want to like just, half-ass it and leave it. But man, it's a pain. So we'll go back to here where if neighbors is 0, because I do really want to understand what's going on. I could always just go copy everything over mine and be like, it's magically better. Maybe I'm being too harsh on it right now. Mute I, U size 0, Y, so it's top Y, bottom Y. I will copy this block here. It's conditional as a starting point. I'll copy over a couple areas which I think are prone to errors, stuff like that, just to make sure. I mean, we already wrote it, but I would like to notice what the problem is. For O and options.iter, for I and O.iter, options to check, insert star I. Let mute possible options, new chunk for new chunk index in options to check.iter. Let mute possible is true. For O and options.iter, if O does not contain new chunk index, then we set possible to false. If it's possible, then we push new chunk index. If possible options is empty, we are sad and self.possible is false. We return true. Else, new chunk index equal, if possible options.len is 1, 0, else, do that roll. That looks fine to me. And then we have basically the same stuff here. I think I copied the right amount. We have that same stuff there. There's another thing we're going to be changing in a moment, which is going to make it look different as well. But I want to go back and I want to grab let's do another run here. Let's just see what we get. Yeah, like there's so few of these that are connecting properly, which just seems wrong to me. I feel like we should have more. Look at that. Yeah, that can't be. Let me scroll back down on their animation and see how big was their play area at least. They did get a pretty small play area. It wasn't that small, but they did get a pretty small play area. I might just be overreacting. See what we get here this time. They probably had like, I don't know, 8 to 10 tiles, 8 to 10 sections that were connected. That one was none. And there's a problem. Actually, we can make this better. Actually, that might help. That would help as well. Oops. Okay. Oh, we do need both. Right. All right, let's rerun it. Now we're gonna pick something that's not in a wall, because that's definitely going to call things incorrectly. Okay, come on, like look at that. None of those were placed correct. Like I feel like the constraints aren't properly defined at that point. I feel like you should only place something if it's valid. There was an exit there and it did not place a tile that matched the exit. Like the second tile. Okay, that's a better, okay, that's a little better. We'll run one more. That's more like in line with what's going on the tutorial. Although it still bothers me a bit. I thought we were trying to go for a solution where everything was valid. Maybe we'll be, we're not done. We are going to reduce the chunk size. We're doing a couple extra things. We're not quite done yet. Okay, so the other thing I want to do is change this back to demo 1. And it's unfortunate we got to compile for that. Not a config or anything. See, I just feel like these are goofy looking though. We're getting some matches though. I mean, we got a cool looking little thing there at the end. I feel like I'm looking at theirs and I feel like they have more connected areas though. I want to see what it calls down to. Oh, it called down to something really tiny. Okay, I'm gonna go with what we have then. There's called down to something. Actually, let's click over to the browser and let's take a look. The bottom one will finish first. If you want to just watch the bottom one, it calls down to something relatively small. Anytime now. Boom. Now watch the top one here, and it calls down to something pretty tiny. It looks like there's all kinds of crazy stuff going on, right? And watch this. Yoink. Very small. So I'm actually okay sticking with what we have now. I feel pretty confident that things are laying out. And I mean, it seems close enough to what they're getting, right? So next we're going to reduce the chunk size. We can significantly improve the resulting map, in this case, by reducing our chunk size to 3. So we're going to go in here. And we're going to run that. And let's see what we get. It's going to take a lot longer to generate. But it's cool though, because you also start to notice patterns a little bit, which is obviously the point, but it's pretty cool to see. I'm still going to go out on a limb and guess that Noita uses wave function collapse. I'm just a first guess is that a lot of games use it. I don't know, maybe something like Rogue Legacy uses something like this. I don't know. Games that generate their maps from like predefined rooms seems like a perfect fit for that. We're getting a pretty beefy map thing here. Fill in that top a little bit. You allowed to do that? I think it just went out of the border a little bit. I don't think we're allowed to do that. Maybe we are. I'm interested to see what this calls down into. Yeah, so when I mentioned patterns that start to emerge, you notice like some of the prefab things that are built out in the Rex image, right? And Noita has like specific like sections that show up all the time. If you play the game enough, you start to recognize them. And that's kind of what I mean by, I think a game like that probably uses something very close to this at least. Oh, that was a pretty good map. It called to something pretty large. Be a pain to navigate. But it's cool. Need like a God mode button for just debugging and testing. That'd be nice. All right, so yeah, we got something pretty decent here. I think I was overreacting a little bit because of the initial results. They freaked me out a little bit, but I think we're good. So that's a much more... I expected it was going to be like a perfect solution. I didn't know we were going to still be calling things because I thought we were going to be connecting as much as possible, and we ended up with very small maps. Oh, and it also mentioned we could try it with test 2 as well. I'm going to hold off on that because it takes a long time. But we can see the results here. We could see both, and both of them are getting ready to complete, so we can just let them both play out real quick on here. What you just saw me do was the top here with number 1. And the bottom one here, which looks like it's going to finish maybe first. It's hard to tell. Bottom one here is with the square rooms. Oh no, they're going to finish about the same. Watch them both. It's so fast. I know. You can pause the video on YouTube. Alrighty. So once again, it's an interesting and playable map. The problem is that we've got such a small chunk size that there aren't really that many interesting options for adjacency. 3x3 grids really limits the amount of variability you can have on your map. So we'll try test one with a chunk size of 5. Okay, there we go. So I'll do that. We'll generate it on my end. It also takes very long to generate, but we have to remember it's not actually taking that long to generate. It's taking a long time to play back because of the sheer number of snapshots. So the larger the chunk size, the fewer snapshots it has to take. Yeah, this is actually turning out like it's pretty interesting. We have an interesting wall that just formed right here, though. So that's going to be called that little room there. Actually, that's an interesting thing. We should. No, I don't know. Never mind. If we did have like an open space that we were trapped in, it would call like the entire map. And then we just have stairs in a tiny little circle or something. I talked about that earlier near the beginning. That's pretty cool. Okay, I can accept that. All right. That's more like it. It's not dissimilar from a map we might try and generate in another fashion. So now we're going to take advantage of the ability to read other map types. Rather than loading one of our XP files, let's feed in the results of a cellular automata run and use that as the seed with a large 8 chunk. This is surprisingly easy with the structure we have. In our build function, okay, so we're just going to do that. So we're going to say chunk size 8 and let mute CA super cellular automata builder new 0, and we're going to say build map. We're going to get the map for t in self.map.tiles.itermute if t equals downstairs. Am I the only one that... Oh, that works. I tend to think more in iterators these days. Itermute dot filter, and then I have to double deref though. Oops, not that. And then if we just want to apply it to everything that made it through the filter, then just for each. That'd also not be fine. Yeah, I thought so. I mean, that would also be fine. I don't know, maybe I'm weird, but I've started to find this more readable, basically. You could also do a reference here, and it should go to a single ref, like that. Oh no, we can't do that, my bad. Ah, that's fine. I don't mind the double deref. That's another way we could have done it. I kind of like that because we've just basically give us everything that is a downstairs, and then for whatever made it through that filter, turn it into a floor. Whatever you prefer. We'll stick with what they have in the tutorial though. So we're removing downstairs. The cellular automata generator will place one, and we don't want stairs everywhere. Gives a very pleasing result. So we'll run it now, and we'll see what it looks like. So that is now our map, and we're going to use that map. No, hold on. This part here. Maybe we'll do it down here after we load the patterns. Maybe we'll do it here. Because otherwise we're just overwriting the map. No, wait a minute. Oh, no, that's right, that's right. That's where we want it. I forgot. No, what we're doing is self.map is our seed for the build patterns. Here we load in the Rex stuff. We don't want to do that. Okay, now it makes sense. Okay. So let's run it and let's see what we get. And you know what I like about this? We get it's a random cellular automata map every time as well. So it's very different every time. I like this a lot more. Yeah, that's more like it. Now we're getting to where I wanted to be. That's pretty cool. You're pretty good. Looks like a lot of this one's going to be usable. Like a whole lot, right? Am I looking at it wrong? No, yeah, it's like almost all of it. I like that. I really like that. Okay. Back to browser because we're just about done now, kind of. And they're fixing one of the problems that I had with it so far. Good. Notice that we're removing the stairs. Yep, and we can see their example real quick. Boom. Improving adjacency and increasing the risk of rejection. What we already have is quite a workable solution. You can make decent maps with it, especially when you use other generators as the seed. On winding jigsaw maps, it's not generating the adjacency we'd like. There's a small risk by making the matcher more specific that we will see some failures, but let's give it a go anyway. In our code that builds a compatibility matrix, find the comment "there's no exits on this side" and replace the section with this code. Did I make that exit? I don't remember. If not has any, that's what I'm looking for. At least we'll see if that's what I'm looking for. Solver. Nothing nearby. Wait, not a compatibility matrix, not the solver. So constraints, right? That's probably why I don't remember that comment now. Yeah, there's no exits on this side. So if not has any, instead of this, we're going to say All right, quick breakdown of that. Match only if the other side also has no exits. So matching exit count, we literally just get an iterator over the opposite's exits, the potential exits on the opposite wall of our current wall. Right? So if we're looking at our north wall, we want to look at our matching partner's south wall, right? And we filter that. It's a Boolean, so we're just double dereferencing that, and we're just checking to see if they're all false. There's another way we can do that, by the way, because we want them to all be false. We can basically, I'm surprised Clippy doesn't notice something like that. So we, instead of counting, we don't even have to filter. Dot all. And if every element of the iterator matches a predicate. So actually, we want them to all be false. Right. I got to make sure I'm reading it correctly, because I think I might need to flip it. No, if they're all not true, then we're good. So then we would basically say, if that, then C.compatible with direction.push J. Either way, to me, it gets a little confusing. So we don't even need the count at that point, right? So, oh, we don't need the double. Yeah. So if potential exits, you iterate over it and you say all of them have to be false. Another way I kind of prefer it is that, because to me that's a little more readable. Nodding equality checks against false can be replaced by a negation. See, but I kind of prefer wrapped it up for us. That's the same thing though. It's equivalent to the other thing, and to me, it is a bit cleaner. Rather than storing a count and checking against a count, we should be able to do that. And it should be nice. So we'll do a couple other checks here. Let me click back over to OBS so I can see the nice full screen. Remember, I'm not expanding the game when it's launching on these builds here. So what I'm seeing is a really tiny thing on my monitor, but if I look at OBS, I see a much larger image. Yeah, it definitely to me looks like it's making a more together map. Oh, it's sick how some of that's coming together. So let's go back over here. And where is it at? What do we want to go back to? I'll go back to 7 and yoink. Demo 1. I don't even care if that other stuff is unused. I'll just do a quick cellular automata and then we'll replace the map. It's fine. It's all good. Oh yeah. Well, we'll see. There's some disconnections still. It's not going to be perfect. What? Oh, it failed. There are 83 patterns. Oh, no, it's not possible. You see it in the console on the bottom right there. Okay, that worked a bit better. It did fail, but it worked a bit better. What's up, Jaeger? I got a bit of a tiny map there. Let me take a look real quick. It doesn't look very good with the jigsaws anymore, so let's try the jigsaws. Might as well take a look at them. Just because there aren't a lot of tiles to make a good pattern, to make good maps with. So I want to see what it looks like, though. Wouldn't be surprised if we get some failures by doing this. Oh no, we got something. Yeah, it's okay. Change this back. Let's get rid of this again. Let's go back to the cellular automata seed. And we'll do, is it 8? Or is it 5? I think it was 8 for the cellular automata. Let's go back to that. Let me run it. It's 8. And this is actually my favorite one. I didn't really make the connection earlier on how we could just use any map type as a seed. This works pretty well. I like it. We did fail that one, so it's regenerating a new one now. Looks really jumbled at the moment. All right, there's our final map. Cool, I like it. All right, so now let's wrap this big old beefy lesson up. 4 hours in. Still a little bit more to go, but it's not bad. So what we're going to do is we're going to offer different build options to the game, which is what we've been doing in the other lessons, in the other chapters as well recently, making multiple constructors, right? So we're going to offer 3 modes to our random builder function: test map, just the Rex paint map, and derived, run on an existing algorithm. That's 2 modes. Test map and derived are 2 modes. Okay. So we're gonna do waveform mode. It's probably a typo from they might have changed things as they were going. So we're gonna go up here to where we made the waveform collapse builder, and we're gonna give ourselves this waveform mode. I don't need to write an enum myself. We've made enums before. Let's just copy that one. So we have test map and derived, and then I wonder if derived is going to randomly pick all the different ones. That'll be cool. We'll extend our new constructor to include these. Well, actually, we need to do derive from on the struct and mode. So mode, waveform mode, and derive from option box dyn map builder. So we're just going to take in a map builder, and we're going to take in waveform mode. This is going to be new depth, mode, waveform mode, and derive from option box dyn map builder. And then we'll populate these things just like that. Sweet. Alrighty. Then we'll add some functionality into the top of our build function. So before we even do the RNG, if self.mode equal waveform mode test map, and we'll do this bit here. I think it's a carbon copy. And we'll double check. It is demo 1, so we'll switch to demo 1, of course. Why is there a return there? That doesn't seem right. I don't know if we're supposed to put a return there. What do I know? Self.map, we load, then we take a snapshot. And we return. That's goofy. Oh, I think it's literally just supposed to load it and we're not actually generating with it. Oh, okay. And let mute RNG, then we do all that, and then chunk size is 8, and then we do a pre-builder. Basically the cellular automata code. We're doing it for the we're doing it for this pre-builder, which is just any type of map builder now. And self.map.tiles.iter mute .filter. We're gonna do it my way. T star T equals tile type downstairs. Dot for each. There should only be one stair, but we'll do for each. Otherwise, we could just get the first thing out of it and be happy. T star T equals tile type floor. Remove that. And then we take a snapshot, which we're already doing. We'll add a couple constructors to make it easy. I don't care enough to type those out. Just test map and derived map. And we have one of them calls it with the waveform mode test map, one of them and does no deriving. The other one does waveform mode derived and gives it some builder. So then we're going to modify our random builder in mod.rs to sometimes run the test map and sometimes run wave function collapse on whatever map we've created. So we're going to go into the map builder thing here. We're going to plop this over it. So basically, oh, it got beefy now. So basically, what we're doing now is we're not actually using the map we generate. Right? So what we're actually doing is we generate a map of any type, and then we do a roll to decide if we want to do waveform collapse on whatever we got. Although I do want to, we sometimes will get the test map. So then in that case, we actually will use the test map to make a derived map from it. So it's possible we get the test map we can play on, or we get the test map and it gets scrambled into a waveform collapse thing. So that actually works out pretty well. The tutorial says that's quite a change. We roll a 17-sided dice, wouldn't it be nice if those really existed, and pick a builder as before, but with the option to use the XP file from WFC test1.xp. We store it in result. Then we roll a 1d3. If it comes up with a 1, we wrap the builder in the waveform collapse builder in derived mode. So it'll take the original map and rebuild it with wave function collapse. Effectively, we just added another 17 options. But what if I don't care about that? Hear me out. Actually, I just need this. What if I just want to do that? And just scramble it no matter what? I want to see like some interesting stuff real quick. I think it would have been cool to actually not make the chunk size constant. This is Voronoi Hive map. It looks like it. It generates that first one a bit too fast. It's hard to tell. I almost want to put a log statement in there. I like it. I want to see like a BSP interior. Who knows? This might be it. I don't know what this is. Oh no, is this the test map? We have that circle over there. You know what we really do if I want to force it, we could just say, where is BSP interior? Oh, is it down there? There it is. I could just be really, really lazy and do this. I don't care. Don't be mad. Let's see what a BSP interior of all things looks like. I think it'll be interesting. It's going to be very, very open. That's why I'm curious. Oh, that's goofy. I kind of like it. That's goofy looking, isn't it? Any other ones to check out? Drunkard's Walk with fat passages. I kind of like that one. You notice that pattern up there at the top repeated a few times really quickly. And that's not necessarily bad. That's the thing that happened. Like I mentioned Loeta, you see that kind of thing happening in those games. We got the same thing happening like 3 times. It didn't work very well. Well, it is what it is. Okay. Back to this. Let's run it. See what we get. I'm pretty happy. Oh, we're getting one. We rolled the dice and we made it. This is only a 1 in 3. Sometimes even on like Caves of Cud, you walk into an area and it's actually pretty small. Like I'm thinking of Red Rock. You get into some floors and they're pretty open. This is pretty open. I think it would be cool though to also vary the chunk size a little bit. Maybe even tweak it per algorithm. Let's see. Oh, we're just getting a regular Drunkard's Walk. This is wave function collapse map generation. Well, kind of. We have 17 different possible maps we can roll. And then there's a 1 in 3 chance of doing wave function collapse on whatever we get. So each one of these builders, it goes ahead and actually like builds a map and everything, right? So we get like a BSP, binary space partitioning dungeon, or binary space partitioning interior, cellular automata, whatever. So we get whatever kind of map builder we roll. We store that in a result, and then a 1 in 3 chance of using that result to seed a wave function collapse, which was the point of today's session. So this is a regular Voronoi hive map here. We're not collapsing it. So a Voronoi hive map, you see these two Voronoi cell builder. Oh, no, I'm covering them right now. On my screen, I'm not. These two Voronoi cell builders here, it was one of those. And then sometimes, like if I just brute force it and say, just make a Voronoi, if you roll the dice, I don't care, just overwrite the result we have. If we see a wave function collapse happening, it'll actually be using the Voronoi map that it builds. This is not wave function, this is diffusion limited aggregation here. With the walk outwards settings. Let's get another wave function collapse on that Voronoi. This is a regular Voronoi, another one. Here we go. So now we're doing a Voronoi, but we're doing wave function collapse on it, which again was the point of this session. We're just wrapping up, basically. Oh, we called a little bit off the edges there. I like it. So back over here, and we're almost done. So yeah, 17-sided dice. Yep, we do all the good stuff. Next, it is cleaning up dead code warnings. Take a moment to do a little housekeeping on the code. There are quite a few warnings in the project when you compile. Almost all this function is never used or equivalent since we're building a library of map builders, so it's okay to not always call the constructors. You can add an annotation above a function definition, allow dead code. I'll do that on my own time if I care enough. So in the drunkard walk, they have an allow dead code on the new function that's no longer really being used. I've gone through and applied these where necessary. Cleaning up unused embedded files. So since we're not using test2 anymore, remove it from the assets. It saves a little bit of space in the resulting binary and makes the CPU's cache a little nicer. So I guess I'll do that real quick. Not difficult. Let's see. Where is it at? Rex assets. Just literally get rid of demo 2. And everything else should be fine. Boom, cargo run. What do we get? Yeah, we got a very quick test map. We can run around it. Ooh, I got a bad spawn though. Did we break our spawn code? I might have broke the spawn code. Also, nothing... You know what might be happening? Nothing seems to have spawned. Oh, I know why. I know this test map doesn't actually spawn anything. We return immediately if we do the test map. So I might want to add proper spawning and stuff to it. We don't even have stairs. If we spawn the test map, it's unwinnable. We don't have stairs, so I'll run around and I'll eventually starve to death. All right. How's it going for you, by the way? You said you were ill. Hope you're doing better, at least a little bit. And this wave function collapse, it's not too bad. This is the longest chapter so far. but it's not that bad. It's just there's a lot of boilerplate housekeeping kind of stuff. We're starving. I'm just waiting until we starve to death. And another fun thing that we've never really updated or changed is that we bleed when we take starving damage. We bleed. I think it'd be nice to add different damage types. And if you're taking starving damage, maybe you don't bleed. Anytime now. Ah, there we go. It's like playing Snake. Oh, there we go. Alrighty. Cool. So let's do, since this was such a beefy boy, such a beefy section, let's recap the high level again of what's actually going on here before I wrap up, even though it's been over 4 hours. Recap the high level of the algorithm, because it's actually not that bad. So the idea of wave function collapse is, let's just say we have some kind of a grid. You know, we have a chessboard, you know, a typical grid. We have our tiles, and we have some kind of prefabricated assets that we're using to populate those tiles. So the easy high level example I keep going back to is maybe a tile can be sand, water, grass, or trees or mountains. What we do is we define some constraints on each tile type. So if we pick sand, the constraints on sand are that sand can only be next to water or grass tiles. And that's an example constraint. Grass can be next to trees or mountains or sand. So grass has 3 things it can be next to. So then we randomly, and those are just 2 of the examples. So then we randomly pick a tile in the map, in our grid, and we randomly assign it something. Let's say we pick sand. Then all of the neighboring tiles are now, they have been restricted in what they can be, because sand can only be adjacent to water or grass. So the neighboring tiles on that sand tile we just picked have now been reduced to a domain of only 3. It could be another sand, it could be water, or it could be grass. So then we pick one of those neighboring tiles, some tile that's already had a reduced domain, and we, pick something for it. And let's say we pick water. Well, water can only be next to sand or more water, so the neighboring tiles to it now only have 2 possible options, water or sand, right? And we keep repeating this throughout the map. Somewhere we're going to pick grass, and then grass, well, it can be next to grass, sand, trees, or mountains. So it can actually be next to 4 other things, right? So we basically just keep doing that over the entire map. So what we've done today is we've taken the Rex paint images. This is what we started with. We've taken the Rex paint images here, which basically defined little prefabs, a lot like a sprite sheet. And here we have one of them. Just scrolled to it here. It's a lot like a sprite sheet where we've got these little like different chunks of the map here, and we can basically cut this thing up into little chunks. And now what's notable about this is the chunks are not actually, each one of these rooms, they're not 7 by 7. They're all really different. So when we take our 7 by 7 chunks, we're not actually getting this entire rectangle, this square, right? We're just cutting 7 by 7 chunks out of this, and whatever we get is what we get. Or if we do 5 by 5s or whatever. So we end up with some very weird and funky shapes, but we basically cut this up kind of like a sprite sheet, and then we build constraints from the shapes that we get, from the patterns that we get. And we basically determine the possible exit tiles from a map, and we try to match those up with entrance tiles to another pattern. And that's basically how we generate our maps. So we have that sheet there, and we have this other one here, which is just a couple basic ones: a single entrance, a dual, a triple, and a quad. So we have those simple tiles there, and then we can do symmetry and all that to get the other options where we have like where we're flipping the single entrance to be on the top or the bottom or whatever, right? So basically, by doing that, generating the constraints and then running it through a solver, which basically says, run that algorithm I just described. Pick a random tile, assign it a random pattern that we've developed from whatever our starting seed was. So imagine we're using this stuff here. Pick a random chunk that we, made from here, and then go through and look for things that fit the constraints now. What's something that can neighbor the chunk that we picked? So then the other example that we were just doing here at the end was, well, it doesn't have to be something that we loaded in from a map like this. It can also be another map that we've generated. So it could be a cellular automata map, a binary space partitioning map. It can be a maze or labyrinth, right? It can be Drunkard's Walk. It can be any of these other algorithms, Voronoi Hive. Any of those algorithms have also produced maps. So if we feed that in, our algorithm will chop it up into little chunks and figure out how it can link things together. And then thus we get interesting maps that basically, again, doubles the amount of maps we already had. Pretty cool stuff. There was a moment here where I was a little worried and I thought something was not looking great. But as we tweaked things there near the end, it got a lot better, a lot more interesting. So I'm pretty happy with it now. This is one I've been looking forward to a lot ever since I first learned about it a couple months ago. And I've been really looking forward to delving into this a little bit. As mentioned, a lot of games use this. Caves of Cud uses it. It was mentioned in the tutorial. I would bet that games like Noita use it. They probably have a bit stronger constraints to make the levels more, to make the world more navigable with less need to call pieces, because their world is pretty consistent in a game like Noita. But it probably uses something along these lines. I don't actually know that for a fact, but I know that the game does use prefab like structures and stuff, and that would kind of fit with what we're doing here. So we actually do have prefabs and sectionals and stuff coming up next. So let's take a quick look at that. I tend to like preview the next section. So we're going to have like handcrafted levels and level sections, and we're going to be talking about like vaults and stuff. That's the next one actually, but handcrafted rooms. So that's cool stuff. Sometimes a room fits a vault. That's cool. So we're going to end up doing some cleanup next time. Some refactoring, and then it looks like we have the demo map, populating the test map with prefabbed entities. So, oh yeah, this is cool. I like it. Uh-oh. It froze up a little bit. Rex-free prefabs. That hurts my eyes. That does not hurt my eyes. Ah, so look at this. We have a cave and a fortification to the side. Interesting. So yeah, kind of like the way this one's going to go, but it's going to be another big old beefy boy, and that's good because next time will be Monday, whatever day it is. I don't know what the date is. Let's see. The 26th of December, and I don't have to work. I don't have to work at all that week. So I don't have to worry so much about like scheduling and all that. I can start a bit earlier. We can have another big old beefy boy session to get these prefabs and stuff. Then vaults are a little bit shorter, so we're shortening back up a bit. But this is getting really interesting. I'm really happy with this. This is going to be really useful, really helpful as I go forward into the implementing some of these things in my own projects. Alrighty, so that's enough of me rambling. This went on for a long time, but yeah, I mean, we knew it was going to be big. I'm, again, really happy with the way it ended up turning out. I think it's really interesting. I think it would be cool to maybe even be more strict on our constraints, but that would also make finding solutions more difficult. I think it's tough. Like it's fine to cull, but I don't like really tiny maps that we sometimes occasionally get. But whatever, right? It's being picky, and I don't even know how some of this is going to come together because if we skip way forward again, we have a town, right? So we're getting to a point at some point where we're straight up making like towns and stuff. So we have buildings going on and roads. I know we're making little roads and stuff. So I think it's going to be really interesting to see how all this pieces together in the coming weeks. So thank you to anyone who showed up, whether you're lurking or chatting or whatever. I really appreciate it. If you like coding, if you like, Caves of Cud came up a couple times. I am streaming that. That's my Friday night, Saturday night stream. If you like Dwarf Fortress, which I guess goes along with this as well. Or I'm also playing Star Ocean right now. I play all kinds of games. Or if you just want to see more coding, hit that follow button. I do these Monday, Wednesday. You could also head over to YouTube, or if you're watching this in the future on YouTube, congrats on being in the future. Do all the fun stuff while you're over there. Like, subscribe, notification bell, leave a comment. I do read my comments. These streams go up 2 weeks after they go live, rather. I put them on there beforehand, but they don't go public until 2 weeks after this stream here. So you're going to be a couple weeks behind. But it's another place to watch them if you can't be here and you want to see what's going on. Also, if you have trouble with like the Twitch notifications or anything, you can follow me on Twitter where I do tweet every time I go live, and hit that notification bell there and you'll get notified and it'll be all good. You'll be happy that you'll be able to catch the stream, right? Alrighty, that's enough of that. I don't think I have much else to say. We closed out the session here. I did skip one little thing at the end where it was removing the dead code. I don't care that much. I think in some of those cases, I deleted those unused constructors anyway. So if we're not using it, I'm going to get rid of it. And so in those cases, it's like whatever. I think we're in a good spot though. And I'm excited about next time. I'm excited about more Dwarf Fortress on tomorrow's stream. So until then, have a good day, have a good night, whatever it is, wherever you're at. Take it easy.
Oh no!